Okay, well, let's go. So welcome, big welcome to everyone. Welcome to the first HDR UK synthetic data special interest group. So my name is Neil Tobias. I'm Professor of Pathology by background and the Chief Research Information Officer at Great Ormond Street Hospital. And I'm also the Chief Data Officer for HDR UK. And I'm just going to give a minute or two of background as to how we kind of got to this meeting. And then I'm going to pass over to Aidan, who's going to chair the meeting. So my kind of interest in synthetic data started a couple of years ago when we were really just trying to do some projects with students with data at GOSH, and particularly around rare diseases, where we thought, wouldn't it be nice if instead of actually giving them this actual data, we could provide students with data to play with that looks like GOSH data. And in a very naive way, we thought, how hard can this be? Well, it turns out extremely hard. And that's why the whole area, I think, of synthetic health data is becoming more and more exciting and interesting, because we tried playing around with a few approaches for some sort of distribution type data and for some time series data. And then we started just bumping into other people at meetings who said, oh, we're trying to do this. It's slightly different to you. We're doing this with synthetic data. And what we found is that there was lots of people doing bits of work, and there was quite a lot, of course, published on this from the sort of computer and data science perspective, but it was really hard to find out who was doing what in this space. So from the HDR UK perspective, we thought, wouldn't it be useful, perhaps, to get a group together of people that are all interested in synthetic health data, just to almost have a little bit of a community. So we had a very informal meeting, which was really just of a kind of a few mates who knew each other a couple of months ago, and came up with the idea of saying, would it be good to see if there's interest in a synthetic data kind of special interest group, which would act to do a couple of things. One just being to sort of, if you like, map the landscape of what everyone is doing in this space, and also to just set up some networking from people that are interested in similar areas. And I'm delighted to say that this went from a small meeting where we were expecting about 20 people to over 160 people who registered for this, which is why it's turned into a webinar rather than just a normal kind of Zoom call, which is what we had thought originally. However, we thought it might be useful to just get some speakers who are actively using synthetic data to talk about various aspects, and we can hang some of the discussions around that. So I'm going to finish there. I'm going to pass over now to Aidan, who is going to chair the meeting, and over to you, Aidan.
Many thanks, Neil, and many thanks to all of you for registering for this event. And as Neil has said, our main hope for this meeting is, first of all, to understand the current UK health data landscape in this space around synthetic or the generation of synthetic healthcare data sets. So we're really keen to learn from you, the attendees today, as to the range of activities going on, particularly in the UK around this space. And what we're really hoping for then is at the end of this meeting, after some reflection afterwards, that at Health Data Research UK, we'll be able to, I guess, better navigate this landscape and to see what the challenges are and the opportunities to bring together a community of researchers from a variety of backgrounds to really try and accelerate the uptake of synthetic healthcare data sets. But of course, there's lots for us to learn in this, and this will be very much a joint learning experience. And Clara, could you move us on to the next slide, please? Thank you very much. So this is our program for today, and I hope that one of the things that will strike you right out from this is that we've got speakers from a variety of different backgrounds, from data custodians to academics on the health data science side, to clinical academics, to colleagues from NHSX as well. So we hope that we've captured a nice broad range of different backgrounds and entities who've got an interest around the synthetic data generation, particularly with respect to healthcare data sets. So I'm very much looking forward to learning from the, I think, the excellent and very exciting range of speakers that we have. And again, I'd like to reach out to you, the attendees. We're very keen to make this as interactive as we possibly can for a webinar. So particularly if you've got any questions for the speakers, please use the Q&A function. And if Clara could take us to the next slide, we're also keen to use the Slido.com website, whereby we'll be asking questions in between various talks to try and get you, the attendee, your feedback and input to help guide us through this, first of all, workshop, and also helping us plan what to do afterwards. And to give this a little go, I would like to encourage you now to log on to slido.com or to use the QR code on your screen. You can see then we've got the, it'll ask you for a meeting or event ID. So if you could enter in synthetic -data-912, it should then bring up a screen which will show a question then that simply asks which of the following broad areas would be your priority area of interest regarding synthetic health data. And if you could do that now, that would be very much appreciated, whereby we have asked this particular question. It will just help us gauge your backgrounds, and which can be helpful to keep in mind throughout this particular workshop. And Fran, I believe you're going to share a screen on this. So we can already see on our live tracker that 25 of you have responded, and we'll let the votes come in for a minute. This is our first time of using this, so it's very much a learning experience for us as well. And what we'll do is we'll let that keep ticking away in the background, and we'll revisit it then during the session. I think we'll just leave it up for another 30 seconds. It's actually quite fun seeing the numbers go up and down.
Yeah, well done, Fran. It's quite exciting.
Yes. And thank you to 41 people, 44 people who've now responded. And so we've already actually got an excellent response rate. We've got to run almost a 50% response rate of the people who are currently logged in. So many thanks for responses, and to others, we'd encourage you to log on to the slido.com as well to give your responses. So we're seeing thus far in the early responses a lot of interest then around synthetic patient level electronic health record data. And then with perhaps then other interests around the population level data and time series generation, which so we were hoping that our upcoming speakers will certainly then cover some of these areas, and it's quite helpful for the speakers to have this in mind too. So to keep on schedule, we're going to now move to our first speaker, who is Pooja Miles, who's based at the MHRA, and Pooja has done a huge volume of work then around the CPRD resource, and one of the main reasons we reached out to Pooja is that she and her team have released a synthetic healthcare data set back in the summer, and it's one of the first major such releases that certainly we're aware of, and we were very keen then to have Pooja at this event and to explain essentially a data custodian's view of synthetic healthcare data sets. Over to you, Pooja.
Thanks, Aidan. And now the first thing to say is that while this presentation is titled A Data Custodian's View, I mean, I'm not representing the whole CPRD view. It is a personal view, which is informed by my working within a data custodian organization and my work on synthetic data. Next slide, please. Now, for those of you who may not be aware of CPRD, CPRD stands for the Clinical Practice Research Data Link. It is a UK government health data research service. We are a centre of the MHRA, which I'm sure in the current context, no one is like, or everyone is aware of the MHRA's role. But we've been around collecting and sharing anonymized patient care electronic healthcare records for over 30 years. And there are some metrics on the slide for you, but in total, including patients who might be deceased or transferred out, we have 60 million patients, and we have 16 million currently registered patients, which is about a quarter of the UK population. Could we move to the next slide, please? Now, at this point, and looking at the title of the presentation, you may well have thought that, well, the reason why a data custodian would be interested in synthetic data generation is because there must be data governance reasons, and it's to just make data sharing easier. So you may be surprised to find out that that was not our motivation at all. The motivation was because we are hosted within the MHRA, and the MHRA has a regulatory remit for machine learning algorithms and applications that are used for healthcare purposes, or including clinical decision making or anything else which could be termed as a medical or healthcare application. And one of the concerns there was that you had a lot of innovative stuff which was coming out, sometimes from small health tech companies, sometimes from individual innovators who were really bright, and they wouldn't. And once they wanted to sort of commercialize or even translate their algorithms into something which was practical and implementable in practice, if they had to seek regulation, they didn't quite know how well to demonstrate that the algorithms they had developed were safe and they were effective. Now, traditionally, for those of you who come from a clinical background, a sort of analogous to this might be development of prediction or clinical scoring, severity indices, or other things like that, where it's not always a matter of testing them and validating them using clinical trials, but there was always an element of external validation. Now, for external validation of these algorithms, sometimes the data are available, which is well and good. But in many cases, what these health tech innovators told us was, well, we've developed an app which is collecting very different data. So for example, when they came to CPRD, we can provide anonymized primary care data and linked data from, say, secondary care. We've got PHE data sources, etc. But some of these apps were collecting data directly from patients or, preclinical data, for which CPRD data sources were not the appropriate data sources for external validation. They were not directly comparable. So this is how these conversations started. People said, well, what if we could come up with synthetic data? And these synthetic data could be used to validate these machine learning algorithms that were developed by these innovators. And that was the primary motivation of this work. So I got together with my colleagues in the regulatory divisions. There was an opportunity for some Innovate UK funding, and we said, well, let's just explore this. We were reasonably skeptical at the start, because while synthetic data, the concept has been around for ages, high fidelity synthetic data that could capture all the complex clinical relationships in real data and be used for machine learning algorithm validation, we weren't sure we would be able to achieve that. But we thought, well, sometimes you just have to just dive in, explore that opportunity. And if it didn't work, at least we had been there and we could close the door on that and then look for other alternatives. So once we started on that path, one of the first things that came up in our project steering group was where we had a public representative. They asked us, well, what are you doing about privacy? And we very naively assumed that if we were aiming for 100% artificial data, privacy would not be an issue. But clearly, this was a naive assumption, and we had to then spin up a separate privacy workstream as part of this work. Now, we were very lucky that the same Innovate UK fund grants that had funded us had also funded the ICO Innovation Hub to assist other regulators who had received funding. And so we were able to get advice from them upfront, and I hope there are some people from the ICO Innovation Hub at this meeting today. And we were able to test some of our ideas and seek advice from them on privacy matters. Next slide, please. Now, this project concluded in March 2020, and the key outputs were a validated methodology for generating and evaluating what we are terming as high fidelity synthetic data sets. And what I mean by this is 100% artificial data, which can be used as a proxy for real data. We've also done some clinical validation tests, which means we've given clinicians samples of synthetic patient records and real patient records. And one of the hypotheses we were testing was like that the records of synthetic patient and a real patient should be clinically indistinguishable for a clinician. And we have reported on some of these experiments as well. We were able to experimentally demonstrate that these high fidelity synthetic data sets could be used to both train and validate machine learning algorithms. We had a proof of concept synthetic data set focused on cardiovascular disease risk factors. And subsequently, we were funded by NHSX to release a generate and release a COVID-19 risk factor synthetic data set. Both of these are available via CPRD, and I've included the link there. Next slide, please. Now, I'm not going to talk in detail about the methods. We have published a paper, and we have another one which is in press in computational intelligence. Plus, Alan Tucker, who is going to be talking later, may cover some of these methods briefly. So I'd suggest, even if you have questions about methods, wait till the end, because some of your questions may be answered. Next slide, please. So just briefly to tell you about our brief approach to use to generate synthetic data, because we were interested in developing synthetic data which was high fidelity, but also to support regulation of machine learning algorithms, we wanted an approach that was very transparent, and that, because it's one thing being able to generate synthetic data, but a big question for us was, how do we know that this synthetic data is any good? And so when we developed our synthetic data generation methodology, there was also a parallel synthetic data evaluation framework that went along with it. And for every synthetic data refresh, and we've been doing, there is behind that or underpinning that a really weighty technical report, which includes all these evaluation tests to show that, these are indeed high fidelity data. But essentially what we do is we're running a Bayesian network analysis on the real data, which is the anonymized, what we call ground truth patient data. What it outputs is this kind of network or web that you're seeing on this slide, and each of the circles is a node which represents a data field or a variable. And it is this network that is then the input in the synthetic data generation process. So, which means this is not perturbation of individual level data where we have like randomly, either perturb the data or just randomly added some numbers to the age, etc. It's completely artificial. Next slide, please. Now, as I mentioned before, we hadn't expected there to be any concerns around privacy, especially because of the approach we were taking, because this was not perturbation. This was completely artificial data. But there are genuine privacy concerns that people have. And, the burden of demonstrating or proving to people that we have taken these concerns seriously meant that, we included privacy checks in our evaluation framework. Currently, we're checking for any duplicate records between synthetic and ground truth data. Now, when I say duplicate records, so I mean if there is a patient, so for a particular synthetic patient should not be exactly the duplicate of a real patient, even if it's completely by coincidence. So I'm not talking about an individual data feature because, of course, you will expect duplicates in that. So, there will be people who have heart disease, who don't have heart disease, but this is like the exact duplication of the record. And again, right now we're being very risk averse and we're removing any duplicate records. We have also been undertaking detection and comparison of outliers between synthetic and ground truth data. Next slide, please. we further undertook a very interesting exercise, which we call the motivated intruder simulation exercise, where one person in the research team who hadn't been involved in the synthetic data generation and wasn't really fully aware of our methods, we gave her the synthetic data and we gave her part of the ground truth data, which was used to generate the synthetic data. Because while we knew there was no way of matching exactly a ground truth data patient to a synthetic patient, we did want to test these assumptions and say, well, what if someone could infer characteristics of the ground truth data patient based on the synthetic patient, especially for outlier patients? And so we gave her 2 weeks and we said, well, you're a motivated intruder, try and hack this and try and match a synthetic data patient to someone who is in the ground truth data. And it was really reassuring to see that at the end of it, she was not able to demonstrate with any certainty. Like, there was one patient which she thought, oh, this synthetic data patient could have been generated based on characteristics of this ground truth person, who incidentally is also anonymized. These are anonymized data, so there is a further privacy sort of safeguard in place. But when she looked at the entire record, it wasn't a duplicate. So again, that was a reassuring test. We also had a further risk assessment undertaken by our CPRD information governance specialist. And based on our current risk assessment, we felt that there was no need to remove outliers in the current synthetic data sets, but we will be revisiting this for every synthetic data set generated. So this is not just you've done the test once and it's fine. Every time we're generating the synthetic data set, and in fact, recently, just last week, we refreshed our COVID-19 data set using more ground truth data set. We had to just repeat everything, all the tests again. Also, in light of the ICO Innovation Hub guidance, we introduced access controls for the synthetic data sets. Initially, we thought maybe we can just put these up on the website. It'll be a self-service feature. People could just press a button and download the data. And I think we all agreed, and we subsequently even presented to the National Data Guardian panel. And I think we've all agreed at this point, it is best to be just cautious. And so there is a basic data sharing agreement and some basic checks to access the data. And also, just as another fail-safe, if you're requesting the synthetic data, we will not provide you access to the exact same ground truth data that was used to generate that synthetic data. Next slide, please. So can synthetic data be used instead of real data? Yes, it can be. We've demonstrated experimentally that it can be used as a proxy for real data, but would you want to use this? And what I would say is that my personal view is that if you have access to anonymized real data, which can be accessed with appropriate safeguards in place, that should be the preferred option. And there is an application where you might want to use low to medium fidelity synthetic data, and this could be for sample data sets if you want to illustrate data structures, especially if you're a researcher who wants to understand the data structure first, just to see how difficult it is to sort of handle the data, or you want to use it for training purposes, for training of data, for data management, or just understand the data better before actually applying for a license to access the data, then this low, medium fidelity synthetic data could be used. And that's not very expensive. High fidelity synthetic data generation, however, like the one we have come up with, is very resource intensive. And another assumption that maybe some people may have, and I've heard this, is, oh, synthetic data will obviously be cheaper. No, it's not. High fidelity synthetic data is not cheaper. And so I wouldn't suggest using synthetic data if you have an appropriate data sharing mechanism in place, or it just doesn't make sense. I would focus on applications, and I won't focus on that just because you think it's cheaper, because it's not cheaper. I would focus on applications instead where synthetic data would provide benefit over and above anonymized real data. Next slide, please. And these are some of the synthetic data applications where I feel high fidelity synthetic data would be really valuable. So there are cases when you need larger sample sizes than are available in the ground truth data, or maybe there is a very rare exposure or a rare feature where you need to boost sample sizes. And in one of our papers, which is in press, we have done an experiment to demonstrate this. The other exciting area, and this is the work we are undertaking currently, is that around conditional generation, because you would have heard, and you must have seen in the media, people are always concerned about machine learning algorithms being biased in their performance. Now, if the data they have used for training those machine learning algorithms are inherently biased, you can't really do much with that. So what you want is not an exact replica of that ground truth data, but you want to be able to tweak some of the features in that data to sort of explore these biases and find out how they actually affect the machine learning algorithm performance. Then you possibly have applications in the clinical trials arena. We know that there are many populations that are subgroups that are not typically included in RCTs, which might include pregnant women, it might include the very elderly. And so synthetic patient cohorts could be used to support in silico trials to simulate intervention effects. And similarly, you could also look to high fidelity synthetic data for external control arms for clinical testing from single arm trials. So like, especially when, like in oncology, you have a lot of trials where it just wouldn't be ethical to sort of randomize patients to placebo. So in that case, so often for regulatory purposes, single arm trials will be conducted where everyone gets treatment, but it may be beneficial to add to the robustness of the evidence by having these external control arms. Next, please. So that's the end of my presentation. Aidan, can I hand back to you for questions, please?
That was fabulous. Thank you very much, Pooja. And quite a few questions have come in. I might take a chair's prerogative then and ask a question I'm very curious to ask. Do you view ultimately synthetic data as being almost like a new source of easy to access data to infer new clinical insights? Or is it perhaps to help, for example, methods developers and say junior researchers then to essentially use it as a much easier to access training resource? I'd be just quite curious then to hear your view on that.
So I feel synthetic data could be used in the clinical trials arena, and not just for training purposes. Like, it could offer benefits, as I said, for sample boosting as well, for the in silico trials, for external control arms. Now, we haven't yet conducted those experiments, but again, it's like, if you only had the resource and the time, I'd want to do all of these things, but I definitely feel there is a possibility there.
And if I may just push you a little bit on that then, so because is there a chance then, I know the synthetic data, we're learning some maybe serious confounding structure that we're then just exaggerating or emphasizing, that might then perhaps lead us to perhaps some wrong inferences, and we just simply boost up that sample size, and we might be perhaps boosting the sort of an underlying confounding structure.
You're absolutely right. The risk is there, and which is why we don't take this work lightly. It's generating synthetic data in itself is easy. It is doing those experiments and demonstrating that these are fit for purpose, they're not going to worsen the problem of biases, is more difficult, and that's what takes time.
Yeah. And then, we've got lots of questions, and I'm going to ask these in order. So one asked by Michael Allen then is, could removing duplicate records leave identifiable gaps in the data?
So there is a risk, and it's like there are no black or white answers. So what we are doing is, so far we're running these tests in every synthetic data that we generate. And it's a decision we're going to have to make on that basis. So again, I have seen some synthetic data platforms out there, which is a different model. It is like, it's for people who actually are data controllers. They can upload their data and then it generates synthetic data for them. And there are, privacy utility metrics, which they can then decide what their risk threshold is and choose something appropriate. But it does make automation of this process very difficult. So far, I don't think we have enough of an understanding, as far as I'm aware. I may be wrong. It'll be interesting to see what other speakers say, that we do need to consider it carefully. So when we've run those tests, it's not just even running those technical reports automatically. There is someone who's actually reviewing them and making a decision that this is fine. It is not actually creating a worse problem.
Thank you very much. And then as I'm casting my eyes over the questions, an easy one here asked from one of our colleagues at the Turing Institute is, are your risk assessment design and results publicly available?
Our risk assessment isn't publicly available. And again, there is a reason for this. Initially, we started with people involved in research, we want our research to be open. We want to share everything. But actually, there might be a risk in putting some of these details of the risk assessment online, of making them publicly available, in case there was a malicious element who wanted to use that to sort of like hack into our processes.
And another question's come in, and they're updating here in real time in front of my eyes. It said, just left me then, was one about rare diseases. I'll come back to Hypnotic then. So one question asked by Mark Kelson at Exeter is there a concern that ensuring no synthetic patient data matches the ground truth could also be revealing in some way? So in aggregate, it could tell you something about the ground truth data.
All these are valid questions and all these are concerns we have discussed, which is why it's like, you do have to look. There is a possibility, we can't dismiss it. And so we continue to test. We're definitely not at the end of the road. There are so many experiments we want to undertake.
And I'd like to thank all the attendees, as we're getting lots of questions. This is incredibly helpful just to spark the discussion that we're hoping to have today. So thank you to all the attendees first. And I'm going to unfortunately have to pick just one last question here in the interest of time, and I'm going to pick one from Kai Cooley then, who's asking Pooja, does the Bayesian network approach that your team used, does that cover data generation for rare diseases? As Kaya said, that this is an area which is often hard to cover with a model and can then obviously have additional privacy concerns.
I would say watch this space, because that is one of the experiments we are due to undertake.
Fabulous.
Eden, I was just wondering, because we got loads of really good questions here. So what we'll try and do, if we don't have time to actually cover them off sort of live here, is we'll collate them and either try and cover them at the end or circulate them around to the speakers. We'll find some way of collating the top questions and getting back to the group. So please do keep putting your questions in, even if we don't get time to necessarily discuss them here. It might be the topic of future meetings. Sorry, back to you, Aidan.
That's very helpful, Dave. Thank you. And Pooja, it would be very helpful if you felt you could answer some of the questions as they come up live. I think you might have the ability to do that if you so wish then too. And we'll be having a group discussion at the end. So additional questions for Pooja, if she's hopefully able to make it, we can then hopefully explore these in a little bit more depth. Pooja, thank you very much. That was a brilliant talk and just exactly what we were hoping for. So thank you very, very much. And now next, we're going to have Mihaela van der Schaar from the University of Cambridge speak. So Mihaela has is obviously very active across the health data science community and has done a lot of work. For example, recently has had a very interesting work finders and keepers workshop that I'm sure she'll talk about then around the synthetic healthcare data generation data sets. And we hope this will very nicely complement, so Pooja's obviously give a perspective then from a data custodian or kind of the MHRA CPRD type hat and learned experience from that. And then Mihaela is very active in, for example, the Alan Turing Institute and the like. So this will, I think, very nicely complement them from a technical perspective. Mihaela, thank you very much for agreeing to speak, and we'll hand over to you.
Thank you very much. Yes, so thank you very much for the invitation. What I'm going to try to give next is more a technical view of synthetic data generation and more specifically a machine learning view. So first I'm going to start by asking, why do we, the machine learning researchers, need synthetic data? And secondly, how can we contribute to this effort? I've been working on synthetic data for many years now, and part of the reason behind that is because in order for machine learning to really catalyze the its true potential in transforming medicine, we need to have available to our disposal rich data sets. This is not only a problem in healthcare, of course, it is also a problem in other domains, ranging from education to social justice to finance. And machine learning researchers like me are often hamstrung by a lack of access to high quality data sets. And this is understandable because in all these domains, there are perfectly valid concerns associated with sharing such data, as were highlighted before. I do believe, though, that synthetic data techniques could offer a powerful solution to this if they are designed correctly. Today, I'm going to give a brief overview of some of this work, but if you want to read more about this research agenda and what my lab has done over the last 4 years in this area, please take a look at our website and in particular to this blog, which outlines a variety of the technologies that we have discussed, as well as some of the challenges. So let me start by discussing some of the challenges that have been outlined already and some new ones. So first is this issue of risk, or another way of putting it, of privacy concerns. And the challenge there is that there is no universally accepted way to use privacy, to define privacy. One possible solution that is often used in my community, the machine learning community, is that of differential privacy. But this is one possible solution and has limitations of its own. I'm not going to discuss them today, but at the end of this talk, I'm going to say how you can engage with us and how you can learn more about some of these alternative ideas. Another issue is that, yes, we can say we let the data guardians to determine the privacy that they would like to impose, but often they may not have the technical expertise or know-how to even define privacy. And I'm going to highlight that a little bit later. And this is very worrying because we can say, well, I'm going to define my own data privacy and I'm going to let free people try to hack it. And if they didn't hack it, then we are fine. But this is very worrying and very concerning because, especially since multiple types of synthetic data may end up in the public domain, somebody may be able to triangulate the users, the different patients in this data set, leading to a lot of challenges. Also, if you look at regulatory efforts such as GDPR, HIPAA, they often provide descriptions of privacy in terms of descriptive narrative, rather than a very concrete and mathematically sound and technically checkable way associated with this narrative. Then on the fidelity side, well, how should synthetic data be really evaluated? Because yes, you can add some noise, yes, you can do some type of inference to say, well, this data is sufficiently of high quality because I discovered this association in it. But is this really enough? And how can we really determine faithfulness and quantify faithfulness? And while being mindful that we may generate synthetic data for a variety of purposes. Again, this may lead not to a single definition, but multiple definitions of fidelity. Just to mention the obvious, yeah, we may not only want to compare on a feature by feature basis, but we may want to look at joint distributions of features. And we might want to define fidelity with respect to that. Problems, of course, become even more challenging if we start to talk about time series data. So we really need to consider the use of synthetic data when generating it. It may be that we are interested in understanding, being able to understand the data for epidemiological reasons. We may want to do discovery, so we may want to be able to do causal discovery on these data sets. We may want to do predictions. We may want to do estimation of treatment effects. So different types of goals may come to mind, and synthetic data may be needed for a variety of these goals. For instance, just to mention the healthcare domain, somebody may want to do an analysis of the data set to be able to make a certain type of epidemiological study or report. Again, as I mentioned before, somebody may want to do discovery, but also analytics. As a machine learner, I'm very interested in developing high quality analytics on the basis of the synthetic data. And not only one type of analytics, for instance, predictions or regressions, but just consider the wealth of analytics that one may want to do on a data set such as CPRD, for instance. Time to event analysis, competing risks, time series, estimating individualized treatment effects, all of them may be pertinent analytics. And synthetic data needs to be of high quality with respect to all these types of goals. Just to mention one of them that I'm going to come back later, that of multivariate time series data analysis. It is really hard to capture the temporal correlations consistently across time. So if you look at comorbidities, morbidities, state-of-the-art research in this area, for instance, is looking at developing time series analysis as well as causal graphs over time that tell about individuals developing different types of events and different types of morbidities, of comorbidities at different moments in time. Unraveling that correctly in the time domain and capturing that is a non-trivial task. Also, if you look at the time series setting like CPRD or other data sets, there may be, for instance, issues associated with the privacy, because if you know somebody may show up at the hospital on a particular time scale, and when the next person is coming, even if you are shuffling around the times of this particular set of events, you may want to capture correctly the timing of these events relative to each other, as well as make sure that this doesn't become disclosive. So this is challenging. So what we really need is a range of concepts for data privacy and data fidelity and ground them in reality. And also then teach data guardians who may not be familiar with these concepts about the risks and the benefits. It is really my worry that today many people talk about concepts such as anonymity or identifiability or without a really clear definition. And I think that this is quite dangerous. What have we done so far? We have worked in this area, as I mentioned, for already quite some time. This is not an exhaustive list of our publications. I'm just putting here a few of them. You can see many more on our website. Today, I'm going to just highlight two works, highlighted here in purple, the first and the third. The first for static data, the next one for time series data. So the first paper that I'm going to highlight was done together with a former student of mine, Jin-Sung Yoon, who now works for Google Research, and a colleague of mine, Lydia Dramwright, who is an epidemiologist. And the focus here was really to generate synthetic data that fulfills GDPR privacy requirements. And this work is based on generative adversarial networks, which are very familiar probably to you by now, but make some important innovations on top of this framework. So first, to ensure fidelity, unlike the standard conditional GAN networks, which are conditioning on a set of predetermined variables, in our work, ADS-GAN, we are optimizing a conditioning set for each patient. So we are going to condition on a different set of features for each patient when generating the data. And we'll generate these components for all the entire parameters of the data set, conditioning on different things for each patient as learned through our framework. The advantages of doing that are that we can improve in this way the quality of the synthetic data while ensuring that no feature combination could readily reveal a patient's identity. And this is important, but that doesn't mean that privacy is not remaining still an issue. Privacy concerns are still there, and we would like to, for instance, fulfill GDPR requirements when issuing and generating such synthetic data. The trouble is that GDPR requirements are not formal. They are not well defined. They are descriptive rather than formal. So one proposal that we make in this work is to formally define the requirements by introducing an identifiability metric that closely matches the narrative of GDPR. And for that, we introduce what we call epsilon identifiability. You can see more details in our paper, but this captures the probability that the distance between the closest synthetic observation in the synthetic data set is closer than the distance from the closest real observation. And we will have epsilon identifiability if this probability is less than epsilon. So this is a metric that's formally and mathematically defined in our paper. Then what is important is because we adopt such a metric of identifiability, in other papers we have used stronger ones such as differential privacy. Here we voted on the basis of GDPR privacy guarantees on this epsilon identifiability to train the model in this ADS-GAN that allows us to move away from this differential privacy notion that's very good but very strong, and I define identifiability based on the probability of identification as defined by this epsilon identifiability. This solution then, this generative adversarial network, conditional generative adversarial network, is then trained in such a way that provides high fidelity, but also thereby increasing the benefit of the data, while fulfilling the epsilon identifiability constraint that may be imposed by the owners of the data. This type of analysis then enables us to ensure that really no combinations of features could readily reveal a patient's identity. This is wonderful for the static setting, and if you want stronger guarantees, we have other works, but it's a static setting. In the time series setting, as I mentioned before, things become more complicated. So one could say, well, I could use generative adversarial networks for time series analysis as well, but this is more complicated. And this is the subject of another NeoRIPS paper last year, where we have a method that we call TimeGAN that capitalizes on multiple strands of research in our lab over time, GAN-based methods for sequence generation, but also autoregressive model for sequence prediction, as well as learning high quality representations using deep learning. So this, before I'm going into the brief details of the key ideas, I just want to say that TimeGAN handles both, handles the mixed data setting, where we can generate both static data, like in the previous work, but also time series data. So what are the key ideas? So unlike a completely generative model using, for instance, a GAN over time, which could be trained using solely an unsupervised loss, we are adding here also a supervised loss in addition. So we are going to add a stepwise, at every time step, a stepwise supervised loss using the original data as a supervision. This will explicitly encourage the data to capture the stepwise conditional distribution in the data over time, thereby ensuring high fidelity. This will also take advantage of the fact that there is more information in the training data than simply identifying whether the datum is real or synthetic. And in this way, we can express and learn from the transition dynamics from real sequences and make sure that they are also present in the synthetic data. So this is the reason for introducing a supervised loss in addition to the unsupervised loss. Then the final part of the puzzle is the fact that we don't do that just in the feature setting, but rather in an embedding, by using an embedding network in the latent space, thereby obliging us to learn correct latent representations. So by doing so, we are able to reduce the high dimensionality of the adversarial learning space. So methods that have been built prior to time-GAN, just directly applying generative adversarial networks without such latent representations, have been shown to perform very poorly. And it is because of this high dimensionality associated with this high dimensional time series data. By using such an embedding, we are capitalizing on the fact that the temporal dynamics of even complex systems are often driven by fewer lower dimensional factors of variations, which are learned through the embedding that we are learning here. And we are learning jointly. So we are training these networks jointly on the basis of both the supervised and the reconstruction loss. That being said, Aidan kindly mentioned synthetic data competition. So as you may know, this week, the best venue in AI and machine learning, NeoRIPS, is taking place. So we are all very busy actually with NeoRIPS this week. And as part of NeoRIPS 2020, our lab, together with collaborators from the Amsterdam University Medical Center and Microsoft Research Cambridge, we have run a privacy challenge, which contains hiders, which are people that are generating synthetic data, and seekers, which are providing technology to identify specific types of vulnerabilities of the synthetic data. As part of our organizing team, we also had clinicians from two different locations, the Netherlands and the UK, that were part of our team and have provided us with a lot of feedback. Finally, I'm going to go back to this idea of building possibly a community where one brings data sets, such as CPRD, or in the case of our NeoRIPS competition, we had a very high quality synthetic real data that was used from Amsterdam Medical Center, which represents time series data in the hospital, in the ICU in the Netherlands. If you are familiar to MIMIC, this is a data set similar to MIMIC, but of even better quality and even higher fidelity because it contains many more measurements and at much tighter scale. But what we would like to build is a clearinghouse where people could come with their data sets and generate synthetic data with high fidelity for a variety of usage, whether it's drug discovery, causal inference, running machine learning competitions, doing statistical research, or for instance, developing better insurance schemes. All of this becomes possible if we have high quality data sets, but also make sure that privacy and fidelity are fulfilled. Finally, our lab has been involved in the last couple of months of building an engagement session with the machine learning community interested in a variety of topics in machine learning for healthcare. And the next session, we have one we just had last week, but the one that we are going to have next month in January will be dedicated to synthetic data. So if you are a researcher, this is mainly for young researchers who are interested in machine learning for healthcare, please register to our website and join our next competition discussion with the other researchers. And if you want to get these slides, sorry for not sharing them ahead of time, you can get them from our lab website. And I put here a link. Thank you very much.
That's fabulous, Mihaela. Thank you very much.
Thank you.
For a really thought-provoking presentation, and I'm a very big fan of the hide and seek challenge. That is a very clever concept. And the first thing I'm going to say is that we've got we've been using Slido during this meeting thus far, and Fran has just shared her screen here, whereby we've got another question in Slido, and we thought this is one of the most appropriate places to ask this, inspired by your talk then, and to ask you, the attendees, whether there are some other methods used in other fields that we should consider in the healthcare domain. So we'd love you to put up your ideas in the Slido there while we go through the Q&A with that, Mihaela. And the first question that we've got here through the Q&A, Mihaela, is I think an easy one to start with then. So Emiliano has asked that, is the code for your ADS scan publicly available?
So we have code for almost all these different methods, and I hope ADS GAN is there. So please take a look at our website, at our Bitbucket, where we have all the methods that we have developed. I think most of them are there, inclusively ADS GAN, but if not, please reach out and remind me and we will release that.
Fabulous.
But Time GAN definitely is there. And the stronger version of privacy guarantee, PATE GAN, is there as well. I'm not sure whether ADS GAN is there, but I think it is. So please take a look at our website and let me know if.
All right, I think Emiliano has followed up to say they did take a look, but it doesn't seem to be there, but I'm sure they can get in contact with you. Or
please get in touch and we'll post it there very soon.
Next question is from one of my colleagues at Oxford, Shing Chan, then, who has got a question around the time GAN, and then just wondering, how does it compare against methods based on rough paths, so the type of work that Terry Lyons and others do, whereby do extracting the time series signatures, then training again on the signatures, and then inverse transforming that. And Shing would just like to ask you, what might be the pros and cons of one approach versus the other?
So first, again, this work, Time GAN, is already quite old by now. So it's summer was done. So it appeared in NeoRIPS 2019. So it's more than 1.5 years old. So I just mentioned it because it was the first, I would say, quite robust method for generating time series data. And since then, many methods have been developed. Building generative models, I would say, based on time series data, whether it's rough paths or other methods, is definitely a good idea. Comparing them together in a unified way, this is exactly what our NeoRIPS competition, 2020 competition, has tried to do. We plan to continue and extend this competition for 1 more year. So through the entire year, we hope together with Microsoft and Amsterdam UMC to continue to play the game, let's say, and enable others to compete. So I would say watch that space. And if you or your colleagues, if Terry, whom I know well, or others want to compete in that competition, we hope that they are going to do so.
Yeah. And if I may ask a slightly different question, so I really like the second last slide you presented on a sort of a vision for the future then of how, let's say, technicians and or folk from technical backgrounds, healthcare data providers, health data scientists, epidemiologists, etc., can work together in a vision from the future. And from your point of view, and we would perhaps love a vision in the future where some national data sets might be available synthetically. From your point of view, what do you find as the limitations or barriers in terms of, is it perhaps getting access to working with data custodians, or is it some legal or ethical challenges, or what do you view as maybe some of the largest, maybe possible challenges or barriers that there may or may not be to collaboration at the minute?
So as a machine learner, very interested in developing methods that are truly useful for my clinical collaborators and that could truly empower them, I am eager to work on real data sets such that the methods that I develop can be carefully benchmarked on real data. But as we all know, this is difficult. And I've encountered this problem for the last 7 years that I started to work in this area. This has been a problem all along. So part of my interest in working in synthetic data is I feel that the machine learning community to which I appertain is very much impaired by not having such data sets. That being said, generating synthetic data that is truly high fidelity and has indeed these different types of guarantees is a complicated problem. It's still a research problem, if you like. So I would say, if you are interested in this area, I'm very happy that this workshop was organized, and I hope many others will come. Please engage with us and engage with the machine learning community, where this is a very hot topic, both in terms of methods development, but also where methods are developed that can be truly useful for predictive analytics for healthcare. So I think it will be nice if the different communities join forces in this.
Fabulous. And there were some questions from your colleagues Derek Snow and Martin O'Reilly at the Alan Turing Institute that we had. Unfortunately, time has got the better of us, so I can't ask.
No problem. I would like to invite, if you allow me, to everybody who has questions, not only me, but also some of my students and postdoc working in this area will be available on January 26th, and we're going to go into a lot more technical details. So if anybody here is interested in machine learning and what it can do in synthetic data, please join us there. Thank you.
Fabulous. Thank you very much again for joining us, Nahila. And I think the last question, and should hopefully give us a nice segue then into our next talk, because we would love opportunities for machine learners, etc., then to get access to some real data sets. And I'm very delighted that our next speaker now will be Johnny Pearson from NHSX. And Johnny then will talk us through then the case study that he and his team have been involved with regards to the HES A&E synthetically generated data set. And I'm very much looking forward to your talk, Johnny, and learning from, I guess, your at the coalface experiences that have working with this and the considerations around releasing such data sets. Over to you, Johnny.
Hi, thanks, Aidan. I can't actually start my video at the moment because host is disabled, but you don't overly need to see my face. That's fine. So, yes, I'm Johnny Pearson from NHSX. It would take me 15 minutes just to explain to you how NHSX fits into the NHS alphabet. So if you think of us as the digital arm of NHS England and of DHSC, then that's probably a good way to start. I'm going to talk to you, yes, about an example. It's actually an example from when I used to work in NHS England and Improvement. So it's a couple of years old now. If we go on to the first slide, some context, I'd say that when we start talking about synthetic data, we always start talking with the techniques, quite right, because they're the interesting ones. That's where the area is developing, and that's where most work needs to be done. However, when it actually comes to sharing the data at the end and using the data, the key question is often not how you produce it, but what the end use will be, because that then gives you an idea of some of the expected issues that you may face, and it also you may find that there are limitations to the methodology that you can then apply depending on your use case. So we're going to use SynAE, synthetic A&E, as an example. We'll go through that as quickly as I can because not got a huge amount of time. Then we're going to look at some of the current user cases as well, to try and take out the lessons learned from the synthetic A&E and then couple it with what I think are some of the real user cases of today. Okay, so the SynA&E, it is from a couple of years ago. This is when I was first investigating data science, and as many people do, you end up on the Kaggle website and you get the Titanic data sets. This is a nice data set with lots of features which look realistic, and you can start to play and explore with many of the data sets on that website. And I was sat on top of a whole lot of source data, heads data, which essentially I thought, can we not do something similar? Can we create a synthetic data set that would allow people to explore and play with health data, and that would then enable innovation, because they'd then be able to come with, look at these ideas, look at these nice things I've done with your data. So that was the aim of it. It was to create a completely public facing, large, generic data set that anyone could use. I'll just say at the bottom there, these slides, I'm not going to go into benefits of synthetic data or very much into the details of technical or into privacy definitions, as those will be discussed in other talks today. So we're going to focus on lessons learned around how to actually get the data out the door. Okay, next slide. So in terms of Syn A&E, the first approach that we did was very naive. We had, as I've said, source data augmented with deprivation data and some distance data, so distance from patient's household to provider. We could then take that, and I've called it foggy data erosion here, but this is essentially an auto-anonymization process, or Pooja called it a perturbation process, where yes, you take your data, you go through a series of grouping and transformation to desensitize many of your variables. And then we took the variable which was having the least impact on other variables according to various correlation metrics, such as Pearson's correlation. We took that variable, used sampling with replacement to replace it, and then we investigated what we had done to the data set, and if we had changed every record in some way, and if we could identify any of the original records. We then did an iterative process where we changed multiple variables until we had eroded the data enough to make it appropriate. Now, even though we were able to show that there was no risk of re-identification with modern methods on that data, it was very clear that it was an inappropriate method for a couple of reasons. But the main one is essentially, if you were to take a subset of variables, it's unreasonably high likelihoods that you would actually be looking at real data, even though you wouldn't know it. So this goes against the appropriate usage of the data and the legal reason why it's originally collected. So that was inappropriate. Next slide. We then changed the methodology, and we decided to go for a Bayesian network. Now, the reason we went for erosion to begin with is because we really wanted to keep as much value in the data as possible. And then, so to keep the higher order relationships, which are often unknown, but those are the ones which we were really interested in. So we didn't want to fit a model to begin with. But once we'd come across those previous objections, we applied a Bayesian network. I believe that will be discussed later. So I'll just say that we use the package BNLearn, which I think is the same one that others have used. I would highly recommend it. Nice, intuitive R package there. From that network, you can sample in order to build completely new synthetic records. So the learning from this, I mean, we did get much higher privacy because every record was synthetic, but at the cost of quality. However, the methodology was also very quick and it was very clear, and that's quite important. We were able to discuss the methodology widely with a whole variety of different people that could critique it. So we could be sure that each record was new, so we could then shift all of our focus around all of the worries around IG to the model structure and about if you could identify realistic outliers, which I'll come back to in a second. If you do want to see that data, it's on that link there. That is 60 million A&E records public. It does take quite a while to download. Next slide, please. Okay, so this has already been touched upon a couple of times. Usually the words privacy and fidelity have been used so far. I use privacy and quality with a utility in the middle as well. And these are three considerations that I think it is key that any synthetic project defines at the start, updates all the way throughout, and then publishes as part of its communications. I won't go through them fully, but privacy is, as you'd expect, it's looking at your sensitivity, your variable combinations and identification, and how linkage to other data sets can increase that identification. You then need to set those privacy levels for different user groups. So if you're just doing a small set of users, if it's an organization you're sharing with, but you always need to have a public level privacy setting. And these are not continuous sort of scales of privacy, it's a binary. It is at what point is it unacceptable for a particular user group to have a certain set of data. And by having those unacceptable levels for those different user groups, you're able to come up with various mitigation strategies. So if you are only going to give it out to a certain organization, you still need a mitigation strategy for your public users, because you have to, in any project where you are sharing data, have a strategy for what happens if this is leaked in some way. And so having that privacy set there already is very useful. Okay, once you've got your privacy, you look at utility. What's the end usage of the data? Is the user case fixed? Which I would strongly recommend, because generic user cases are extremely difficult to get past IG. And what does a successful usage of the data look like? What's going to change from that? And the reason for asking all those questions is the two questions further down, because once we know the utility and the usage, you can start to look at individual variables and very much say which variables are key, which ones can we actually do some pre-processing on of some way and reduce the sensitivity within those variables. We should always be working to a minimum data extract at all times. That goes very much against the academic side of me, which says let's take the best that we can possibly make. But actually the GDPR side of me says you have to use only the minimum set of data for the purpose. If your purpose is generic public, then it's a wider set of data. But if it's a specific piece of analysis, then to use the minimum and to pre-process other fields is best practice. So once you've now defined utility, you've got an idea of privacy. We look at quality. Quality is very difficult because the quality metrics, yes, are not defined. For some usages, can an algorithm distinguish between synthetic and real, so such as GANs? Or for others, it might be that the records need to hold realistic values, but there might be some, it might just be about applying a probability model that will allow that, and you don't need to go to the higher order methods in order to actually achieve your utility. Two of the stats metrics that I would recommend for quality, the Williamson statistic is something which we use, which compares variance between the real and synthetic data set over the expected degrees of freedom. So it gives you an idea of appropriate variance versus observed variance. And then the propensity scores from Wearable is another good measure. So then the last things to think about in quality: what's the lowest quality acceptable, what's the highest quality achievable? And then for all of that, that brings us to choosing our method, which may be very much counter to how most people are working, where you're looking at particular methods and seeing what can we do with this. I'm thinking about usage and actually getting data out there. So it's very much what's data going to be used for, go through this process. These are the methods which we could apply. Okay, next slide. Some lessons learned from the synthetic A&E. So apart from having the privacy, utility, quality throughout your whole project, my second biggest lesson was to work in the open. Again, possibly slightly counterintuitive, but essentially by building the methodology in the open, you're able to have critique right from the off before it gets serious. You're able to also be working in best practice ways of working. The way we did this for Syn A&E was to do an open set of blogs for the methodology, and then we did a workshop where we invited a closed group of people to come along, and essentially, as this little cartoon tries to show, you get a completely different perspective on your work. And through that, we were able to establish all the inappropriate things which led us to change the methodology. I would say if you are going to do that workshop idea, allowing a group of people to have a synthetic data set for a day, and at the end of the day to ask them, tell me everything that's wrong with it, is not enough time. So we had this nice closed room where everyone signed a form saying they wouldn't take the data out of the room. However, it would be a much better idea to give them the data for a much longer period of time, because you can't do the work which is required in a workshop setting like that. That was a definite learning point for myself. So if I was to do it now, I would use GitHub and very much share it with a closed group of people through there. I would also encourage that you build your methodology with dummy data. So you're very much saying, here's a dummy real set of data. Here's the synthetic data we've taken from the dummy data. Can you find any issues with the methodology from that? And again, just slowly allow that conversation, that critique to happen. That is the best way to not only be confident in yourself, but also for your IG colleagues who are, basically all of this sharing process is about getting confidence with your end users and your IG colleagues. And if you are doing it stepwise, that's much easier than at the end saying, here's a big data set which has all these potential issues, but could you sign it off for us? Okay, some of the other issues, risk of re-ID. This is obviously one of the key areas where people are very interested in. The learning from that for us was that we could never actually state we were 100% confident, because the argument goes there's advances in the field all the time, and so you never know who's going to come up with an algorithm that can unravel your methodology. However, your IG colleagues will be looking for exactly that statement of 100% confidence. And so the way that we were able to progress was to say that we were 100% confident that we had removed all known risks of re-identification. We didn't use differential privacy for SynA&E, although I highly recommend using it. So using obfuscation and then considering, and this for us was the key learning point, considering how an unraveled model could identify individual cases. And for that, it requires just a very good knowledge of your manifold of your model latent space. So your manifold being all of the possible combinations of variables that you can have in the real data. I would advise spending quite a lot of time on those two topics, on visualizing and understanding your data set at the beginning. And the reason for this is to look at those sporadic areas, those sparse areas where there are rare cases, because those are the ones where if you have a model which is has some overfitting, it will identify those particular areas. And if you then remove, if you had a malicious use that was to remove all off-manifold variables and just look at the areas where the model is particularly highly fitted, then you could start to infer something about the real data which has informed the model. So these are the things which we need to consider. Appropriate use of the data I've already discussed, and so that's about understanding the legality and how the data was collected to begin with, but I'll leave that one there. Communications I'm going to come back to because I've actually put it in the wrong order on the slides. So if we go to the next slide, and I'll talk about actors and threats. So we managed to do a bit of an exercise where we create a data ecosystem. This doesn't take long. This took us 3 hours on a whiteboard, but it's immensely valuable for increasing confidence and showing your thought process around threats. And it just tracks the data from the people that collect the data to all the different people that handle it, to the generation of the synthetic data, and then who can see that. You're able to then characterize all of those actors into different cohorts and essentially look at the threats from those different cohorts. The top threats that we found to share with you: false insights. Yes, people who are using your data inappropriately, who are defining policy of data which doesn't have very high fidelity, for instance. The second risk identified was the anonymization process, if that frankly isn't good enough. So yes, that's essentially, you have to spend a lot of time and energy on your anonymization process. And then the third one, which was a surprise for me, was fear. So this is your, essentially you publish your data and a tabloid picks it up and says, NHS has published 60 million records, how dare they? And all of these things are mitigated by point on the previous slide, which we don't need to go back to, but essentially communications. Having a clear communication strategy, again, if you can do it in steps, slowly introducing the idea, introducing the method, introducing the concerns and how they've been mitigated, and then introducing the data, you're able to have a much easier time and a lot less fear when that data is published. The tests which we used, I've listed some of them there. 5 quality tests, 4 privacy tests. You can see they're all very simple. Pearson correlation to look at your variable relationships and that they've been maintained. Profile comparison, I've mentioned we use the Voris-Williamson statistic. The off-manifold and latent space checks for SynA&E, they were extremely simple. It was simply to check any new variable combinations that had been created. We then had a look at the impact of the data on the end user cases. And then for the privacy, like-for-like comparison wasn't applicable for the Bayesian methods. That was only for the foggy data erosion. But looking for duplicate records between real and synthetic data. So this was mentioned by Pooja earlier, that you can end up with a model that accidentally recreates records. That's called collision testing. Can I find me? Very simple set of ideas. Again, just getting a user to test the data, although as we've heard from Mihaela's talk, not something to rely on, just something to build confidence in. And then the big one for me was the uniqueness of combinations. So this is all the stuff about the checking your manifold and looking for if any outliers have had a recreation forced. So if we've accidentally ended up with a bit of space where we essentially are going to always recreate near real data, because you should pick up your real data with your other checks. But even if it's near real data and someone can then look at if it's off manifold or if just tweaking it up a bit fits the model better, then that might give them an indication of the real data behind the model. Okay, if we carry on to the next slide, I think I'm probably over time. So just to say that these are some of the user needs, which I think people are not always aware of. The first two we're definitely aware of. We've mentioned training data for data analysts. The second one, academia obviously needing very high quality data so that you can do research on data sets which you don't currently have access to. But some of these other ones, being able to have data which you can then build a visualization tool off. So imagine Financial Times using the data in order to show how COVID is spreading. They don't actually need the exact data. They could use synthetic data. So that's purely just helping people to understand the systems a bit better. App infrastructure development is the one which I'm chasing at the moment. So this is very much giving data to people so that they can produce better proof of concepts for apps and tools, or even machine learning algorithms. It would fit into the same category. So this is allowing people to build their model, and then when they bring it to the NHS and actually ask for a serious amount of money, they're able to prove they've already thought and considered about a lot of the data issues, and it's a much faster implementation process to actually put the model onto real data rather than having to go and essentially rewrite your model once you get to see the actual data, which is often the case. 5 there modelers, people looking at evaluation of policy and the impact it might have. Again, they don't actually need the specific real data all the time. They just need data that they can flow through a discrete event simulation or an agent-based model or an economic evaluation in order to show what the impact could then be if they change an earlier lever. And then realistic test data, this is simply about, again, apps and infrastructure. If they're going to fall over, for instance, if your Excel spreadsheet doesn't have enough rows in it, those sorts of tests would all require. So that's not high fidelity synthetic data, that's very low fidelity synthetic data. I'm going to miss the generic tool versus specific data set comment there and just say, we do always need to consider the alternatives to synthetic data. It may not always be the best solution, as I think one of the comments in the questions previously stated. We are investigating importing models into secure data sets and all of those sorts of approaches as well, because they're often more applicable. But there is huge potential for synthetic data, and we haven't quite managed to get to a point where we're really accessing all of that potential yet. I think I'm way over time, so if we just put the last slide up, and I won't even go into it, but those are some of the areas of interest for NHSX at the moment.
Thank you very much, Johnny. That was really fascinating. And one of the questions that came in quite early in your talk was from Jackie, who was asking them if we were to try to explain to a lay person how might we ensure then that the synthetic data reflects real life? And she was given a very specific example then, do we frequently check, for example, portion of data of ethnic minorities? So then I think you've perhaps covered in that then, but could you perhaps elaborate on that just a slight bit more then on the checks you do before releasing a data set?
So again, that depends on your usage, but let's assume that that usage is to have a data set which yes, realistically reflects. And we're putting out a data set which essentially is generic in purpose. So you can use this data set to explore lots of different pieces of analysis based on the data, rather than we've created a data set in order to do a piece of analysis on ethnicity, for instance. So if you've got a generic data set, then surely all of your tests come down to, can my synthetic data set be distinguished from a real data set? Alternatively, you can do a series of tests to say, do the known correlations between the variables reflect the real data ones? Those are the only two tests which I would do to reflect if the data is realistic or not.
Thank you. And then another question we've had come in is from Sarah Payne at the MHRA. Then she was just interested to know whether you involve members of the public or patients then on your SynthAE project.
So we worked with Leeds ODI, and they essentially put out an open blog with an open invite for anybody to come to a workshop where they would be able to have access to the data and then critique it. So that was open. That doesn't mean that we've sought out engagement with public there. So I think the answer probably is no. There was an opportunity, but it was an advertised opportunity, but not a pushed opportunity. And for the NHS, for public engagement, you need to push the opportunity. So I would take that as a valid critique, essentially, that there should have been more public engagement than just the opportunity.
This is a very new space for many of us, and the point of having a workshop and lots of people here is it's useful to get the insights from everyone, attendees, presenters, and all, and we're all jointly learning in this. And then if I could just finish and ask one last, maybe slightly provocative question that was inspired by your second to last slide, then wondering, because you were talking about possible alternatives to synthetic data generation. So it's very clear from your talk, and also Pooja's as well, that synthetic data is definitely not a free resource. It's quite resource intensive. And then is synthetic data potentially worth it, do you think? Or should we perhaps be thinking about other approaches? I think you suggested the federated analysis. So is it worth the effort to generate and go through all the checks on these synthetic data sets?
I mean, take two user cases. One is a data set that represents the real data set exactly, and that we're trying to answer a research question with. The question there is, why can't we get access to the real data? And even not access to real data, why can't a model be created which can be applied to the real data by the data custodians, or sent to the data without the data ever moving? These would seem to be better ways of working, because you're working on the actual data, you're able to still do the analysis. And the synthetic data certainly is quite resource intensive to create. However, if that's not an opportunity, the research still needs to be done. We still need to be able to seek insight from the data. So at the moment, synthetic data has huge potential to sit in that gap. I would prefer a situation where we were doing imported models. So send your model across to the data without ever seeing the data, and then bring it back. In order to develop that model, you'd need some form of synthetic data, but the quality of it wouldn't necessarily have to be that high. For low fidelity user cases, such as app testing or even visualizations, I think that synthetic data has a huge potential to just really speed up innovation and help and support people. And so for that, yes, I think there's huge value, but obviously that is much lower fidelity. So you don't always have to be applying the absolute cutting edge techniques to those cases.
Fabulous. In interest of time there, unfortunately I can't ask any more questions. And I see one has just come up from an anonymous attendee, and perhaps feel free to answer that one in the free text in the Q&A. That'd be great. So Johnny, thank you very much for presenting again, and we might grill you with another couple of questions then towards the end of the group discussion if you're available. And now we'll move on to thinking about, as Michaela said in her talk a little bit earlier, there could be I guess some unique challenges then around the generation of time series events. And one of the most rich forms of time series data comes from a source familiar to many clinicians, the ECG. So in our next talk, we're actually going back to Cambridge again. So we've got Peter Charlton, who will be presenting then around the synthetic generation of complex healthcare data types, specifically sensor data. Over to you, Peter.
Thanks very much. Thank you for the opportunity to speak today. So I'll be presenting on generating synthetic wearable sensor data. The motivation for this talk is in the prevention of cardiovascular disease. In the course of this talk, there will be approximately 3 hospital admissions due to cardiovascular disease, 5 deaths, and it will cost the NHS approximately £250,000. There is a new opportunity in the widespread use of wearables, such as this Apple Watch, to monitor cardiovascular health continuously in daily life. Apple Watches, Fitbits, and many wrist-worn sensors which monitor the heart rate all measure arterial pulse wave, which contains a wealth of information on both the heart and the blood vessels. If this information could be extracted reliably, then potentially it could be used to inform diagnosis and treatment. To introduce myself, my name is Peter Charlton. I'm a biomedical engineer at the University of Cambridge and at City University of London, and I work in collaboration with clinicians such as those at St. Thomas's Hospital here to develop techniques to analyze wearable sensor data and then to try and translate them into clinical practice. In my talk, I'll focus on 3 areas. Firstly, I'll provide an overview of the fundamentals of wearables and how they acquire the arterial pulse wave. I'll then describe our work on generating a database of synthetic pulse waves, and I'll give a couple of pointers for future research directions. So firstly, the importance of wearable data. I think the importance of wearable data came home to me about this time last year when the Apple Heart study was published in the New England Journal of Medicine, and it appeared as though the Apple Watch could be a very helpful tool for identifying atrial fibrillation in daily life. Atrial fibrillation is a common heart arrhythmia, which is responsible for increasing the risk of stroke by 5-fold. There's a standard treatment for it, which is to give anticoagulation to reduce the risk of stroke, but it's difficult to identify, partly because it may not cause symptoms, and partly because it can occur only intermittently. And so wearables provide a new opportunity to detect atrial fibrillation in daily life. Other areas of importance include monitoring health throughout daily life, for research to track people longitudinally and allow us to better understand disease. And the benefits of using wearables are that they are widely used already, and broadly, they're accepted. So now to look at how wearables acquire the pulse wave signal. This is called the photoplethysmogram, or PPG for short, and it's the signal that's measured by Fitbits, Apple Watches alike, to monitor the heart rate. Here's a cross-section of the wrist. The sensor consists firstly of an LED, which shines light on the surface of the skin, and a light sensor, which measures the amount of light reflected back from the skin. This is used to produce a PPG signal. As blood flows from the heart into the wrist each heartbeat, the amount of arterial blood in the wrist increases and it attenuates the light, and then it decreases again as the blood leaves the arteries and flows into the microvasculature. So the PPG is primarily influenced by arterial blood pulsations, but it's also influenced by other factors such as venous blood and the tissues. To give 3 examples, so here is a PPG with a fast heart rate of 100 beats per minute. In comparison, this is a slightly slower heart rate, still a regular heart rate. And then thirdly, this is a PPG during atrial fibrillation, where both the beat-to-beat intervals vary and the amplitudes of the pulse waves vary. It's not only the looking at pulse waves over time, which is helpful, but also one individual pulse wave contains information on the cardiovascular system. So for instance, here are PPG pulse waves acquired from young in blue and elderly in red subjects. They're healthy. You can see that the young subject exhibits 2 peaks. The first peak is the instant wave arriving from the heart, and it's thought that the second peak is the reflection of pulse waves from the periphery. There's a time delay between the two because it takes time for the pulse waves to reflect. However, in the elderly subject, their arteries have naturally become stiffer with age, and so this time delay is much shorter, and it appears as though the 2 peaks are now superimposed on one another. The utility of synthetic data. Well, for me as an engineer, my primary use case is in algorithm development. Synthetic data allows me to check the functionality of algorithms across a wide range of conditions, so I can control what the cardiovascular conditions are that result in that particular signal. I can also compare the outputs of algorithms to known reference values, which might otherwise be very difficult to acquire in clinical practice, so they might require invasive measurements, for instance. Synthetic data can be used to inform the design of clinical studies, and perhaps in the future, it could be used to assess algorithm performance directly without the need for a clinical study. So I'll now discuss our work on creating a synthetic pulse wave database. Our aims were firstly, to create a database of simulated PPG pulse waves representative of healthy adults. Secondly, to verify it by comparing it with real data. And thirdly, to investigate the potential utility of PPG pulse waves for assessing arterial stiffness. So this is the approach we used to simulate PPG pulse waves. We had a model of blood flow through the major arteries, which we adapted by adding on the functionality to output PPG pulse waves. On the left, the model takes as inputs the cardiovascular properties of the heart, the arteries, and the microvasculature. It then simulates pulse waves, allowing one to generate PPG pulse waves at a range of common measurement sites throughout the body. The first challenge was to specify the input properties to allow us to model healthy aging. To do this, we performed a literature review of how each of the input properties changes with age. So for instance, for stroke volume here, we found that it decreases with age, and this was based on an analysis of 10 publications. We then extracted mean and standard deviation values shown in solid black and dashed black respectively on these plots for each of the input parameters. So for instance, if we wanted a baseline 45-year-old, then we took the mean value for each input property for 45-year-olds. And then if we wanted to model normal variation, then we took plus or minus 1 standard deviation, the value of each property. Firstly, we ran simulations for virtual subjects by varying properties independently. And then secondly, in an attempt to generate pulse waves which were representative of a sample, we took all possible combinations of the input parameters, here shown for just 2. So this resulted in a database of 4,374 virtual subjects, each with their own pulse waves. Having generated these pulse waves, we then assessed their physiological plausibility by checking whether their blood pressures were plausible. And we found that just over 10%, 537, were not plausible, and so these were excluded. And this may be because we didn't account for some of the interactions between input parameters. So for instance, if someone has a very high heart rate and stroke volume, they'll have a very high cardiac output. And it may be that it was unreasonable to specify that to the model. So the database, here we have PPG pulse waves for the baseline subjects of 25 to 75 years old in 10-year intervals. We created the database, both exhibiting changes in healthy aging on the left and also normal variation in cardiovascular properties on the right. The database is publicly available at the link below, as is the code used to analyze it. So our next step was to verify the database through comparison with real data. This shows at the top finger PPG pulse waves and below ear PPG pulse waves. On the left from in vivo data acquired from healthy subjects, and on the right from our simulated pulse waves. And it shows how the pulse waves shape change with age. So the finger PPG, you can see that this second peak disappears in the older 55 and 75-year-old simulated subjects. And below for the ear, you can see that the two peaks for a 25-year-old merge to become one for the 75-year-old. We also compared pulse wave indices, which were calculated from the pulse waves. So to demonstrate this, here is a pulse wave for a 25-year-old, and then its first and second derivatives, and typical points that are identified on a pulse wave for analysis. Here is the corresponding 75-year-old pulse wave. And the first index that we looked at was the stiffness index, which is the height of the subject divided by the time delay between the two peaks. We found that it increased in the simulated data on the right with age, just as it does in vivo data. So the trends were similar, even if the absolute values were not exactly the same. We also looked at a second index, the D/A ratio, from the second derivative. And again, we found that this changed in a similar manner to that observed in vivo. It reduced with age. So this gave us some confidence that the database was realistic. Then thirdly, we investigated the potential utility of PPG pulse waves for assessing arterial stiffness, an emerging marker of cardiovascular health. The aim here is to infer the stiffness of the aorta, which is linked to cardiovascular outcomes, from a signal, for instance, measured at the finger, perhaps using a smart ring. On the right are examples of pulse waves from 45-year-old simulated subjects with low and high stiffness. And you can see how the second peak is disappearing in the subject with the higher stiffness. And we used two indices to infer stiffness. Firstly, the stiffness index that I mentioned, calculated from the delay between peaks. And then secondly, the modified aging index, calculated using points on the second derivative. And here are the results plotted as the reference stiffness measurement, the aortic pulse wave velocity on the x-axis, against the index extracted from the PPG pulse wave. And the first thing to notice is that the coefficient of determination R squared across the whole age range, shown in black, is relatively high for both these indices, suggesting that they may have some use for inferring arterial stiffness. However, we found that the stiffness index had greatly reduced performance if you only considered subjects from one particular age range. So for instance, if you were presented with a middle-aged subject and you wanted to know whether or not they were at elevated cardiovascular risk. In contrast, on the right, the modified aging index had an even higher coefficient of determination for that one age range. And the database allows us to look at why this is the case. These plots below show the influence of individual input parameters on the index extracted from the PPG. And so, for instance, for the stiffness index, the pulse wave velocity, the reference measure of stiffness, had a large influence on the stiffness index. But so too did the stroke volume, the large artery diameter, and the peripheral vascular resistance. And the stroke volume and the large artery diameter in particular both changed with age. And so perhaps the change with age observed by the stiffness index was not just due to changes in pulse wave velocity, but was also capturing some of these other changes in input properties. Looking at the modified aging index, the pulse wave velocity was also a strong contributor to this index, but it was also influenced by the heart rate, for instance, which did not change systematically with age. And we believe that this may be in part why it maintained a strong correlation across even a small age range. So to conclude, we've created a publicly available database of PPG pulse waves. We verified it through comparison with in vivo data and observed similar trends between the two. We haven't yet performed qualitative comparisons. And we've demonstrated the utility of the database, firstly for initial algorithm assessment. Secondly, since we knew the reference values that we used to generate the signals, we're able to investigate their origins. And thirdly, the results I've just shown could be used to inform clinical study design. So for instance, if you wanted to see how well those indices performed in reality, you might say, well, we're just going to look at a narrow age range, and we're going to ensure that we capture data in the presence of changes in those input properties, which we expect will influence the estimated index. So the outlook for the future. So a key challenge, of course, is that the simulated data I've just presented were entirely clean, free from noise. In reality, if one tries to acquire this data in daily life, then there is a whole host of influences causing noise in the signals. So here is shown a PPG signal above, relatively clean at rest, and then one whilst walking below, which is much more noisy. So perhaps we should incorporate noise into the model. And secondly, returning to my initial slides on atrial fibrillation, the work I've presented has been on one pulse wave. In the future, I would like to be able to model, for instance, heart arrhythmias and simulate pulse waves in the presence of heart arrhythmias. And this would be particularly relevant at the moment because here in Cambridge, my colleagues and I are conducting a study assessing handheld ECG devices to screen for atrial fibrillation, assessing their cost effectiveness. And we're fortunate that we're quickly acquiring a very large database of ECG signals from which one can infer the timings of individual heartbeats in both normal rhythm and in atrial fibrillation. And so perhaps, given that we are amassing this knowledge of what atrial fibrillation looks like in the target population, we could use that to simulate pulse waves, which could be used to assess the performance of algorithms for detecting atrial fibrillation. With that, I would like to acknowledge my colleagues, the Safer Study team, and the British Heart Foundation who funded this work. And just to recap, we've looked at the fundamentals of wearables, a database generated of synthetic pulse waves, and then future research in the area of atrial fibrillation. More details on the website. Thank you.
That's fabulous, Peter. Thank you very much. It's a subject quite close to my own heart, so I'm a huge fan of the wearables work that you do. And as a matter of curiosity, if I may ask a non-synthetic data generation question, so the SAFER study, how many people are you collecting the handheld ECG data from? And just may I ask why you perhaps did not consider, say, going with a wearable patch for that? Fantastic. So it's planned to acquire data from 40,000 subjects,
So far, the feasibility study has been completed in just over 2,000 subjects, and each of those 40,000 will contribute of the order of 80 ECG recordings each, so a large database. Why are we not using wearables? So an ECG is required for currently to confirm atrial fibrillation. However, we've just received ethical approval for the safer wearable study, in which we will use wearables which acquire both ECG and PPG signals in a much smaller cohort of participants.
Oh, excellent. And then if I may ask a question around, it perhaps covers what you covered then. So by generating or using a rule base to generate synthetic data, in this case it had a focus, as I understand, on, for example, atrial fibrillation. If there are some other close phenotypes to that, I'm trying to think, maybe ventricular tachycardia or one of the 10 or 11 other AF subtypes or close variants of that, how do we deal with challenges then such as that? Do we have to handcraft them for each of the particular subtypes of it, or is there maybe some generic methods we can then use? I'd just love to hear your thoughts on that.
So my instinct would be to say that we have to observe what we're looking to model in real life. And so something like ventricular tachycardia is relatively infrequently observed in comparison to atrial fibrillation. So for us, it would be difficult to model that based upon what we observe. But I think you raise a good point that potentially what might be ideal would be to have a model which was able to simulate pulse waves under any heart rhythm, perhaps with some generic rules. I think that would be a challenge to develop that model.
Yeah. And then one of my colleagues at Health Data Research UK, as you said, Varma then is asking, Peter, have you looked at the electrophysiology cell NL models? Apparently these allow you to parameterize your electrophysiology traces using sensor data.
So I have no experience in it, and it certainly could be very useful. I think it could be useful for if you were able to couple a model, for instance, of the contraction of the atria and ventricles, which may rely on that, with our model of blood flow, then perhaps you could start coming up with a comprehensive model that was able to incorporate not only individual pulse waves, but also a heart rhythm.
And before I say anything else, I'm going to say, Fran, was it possible, Peter, for you to stop sharing your screen? And Fran, I believe, might have a question for us. And I perhaps put her on the spot there now. Actually, I haven't, because she's very ready, as always, because we were very keen then to ask the participants and you, the attendees, if you could perhaps log on to Slido again, because we're very keen to find out what you view as one of the main reasons for generating synthetic healthcare data sets, whether it's to generate new clinical insights or to facilitate training or to help methods development. And Peter, I'd be quite keen to hear what your view might be on this too, if I was to ask this question to you. Or actually, perhaps don't give your answer yet, because I don't want you to influence the results here, because I see Jackie has asked a question here, and I'm just going to paraphrase it. So Jackie Gaff has said, the SAFER study sounds very exciting. So what do we... Oh yeah, so she said, so the data regarding ethnicity groups or biological sex and possibly other variables are in the SAFER data set. She said, then, would it be possible to ascertain differences in risk, presenting symptoms and possible treatments between the groups? And I'm trying to...
Yeah, I'm sure it could be a very fruitful area of research.
So I probably badly paraphrased your question then, Jackie, and I'm sure Peter will answer that in the chat afterwards. And then Peter, I'll just go back to you with one last question. And so if I was to show you the question on the screen of Fran, then what would be your view in this? I'd be quite keen to find out.
my view is useful for all three. So as an engineer, I very much value data for developing algorithms, and a huge synthetic data set is often complementary to a clinical data set. We were able to generate some new insights into how the blood pressure measured at a cuff differs from the central blood pressure next to the heart using this database, to give us new clinical insights into what we're actually measuring in the clinic and how it relates to what the heart experiences. So yes, generating new clinical insights. And then of course, I think it's invaluable for facilitating training. So I am keen, as demonstrated by uploading the code and examples of analyses to accompany this dataset, that others should learn from this work and be able to build on it.
Peter, thank you very much again for presenting, and if there are any other questions for Peter, we'll be able to hopefully grab them again in about 50 minutes time then for the group discussion. So next up, and Fran, thank you very much for showing that the live poll, and thank you to you, the attendees, for filling that out. It's very useful for us. Next up, and we've deliberately interleaved the talks of being focused on methods development, and also then quite focused on particular areas and challenges of releasing some large data sets. And I'm delighted to say, well, we've next got Laura Frayling, who will present some of the, I guess, hands-on experiences then of sharing synthetic data sets in the area of cancer. Over to you, Laura.
Thank you very much for the introduction. I'm really pleased to be here today to talk about our experience with sharing synthetic data at Health Data Insights. My name is Laura Frayling, and I'm a data scientist who started working here about 2 years ago, and I was put straight onto the Simulacrum project. Next slide, please. So I'm going to, throughout this presentation, I will give a brief introduction to Health Data Insight and talk about our experience with synthetic data, specifically the Simulacrum, and then the benefits and challenges that come with that, followed by concluding remarks. Next slide, please. So Health Data Insight is a social enterprise that facilitates improvements in healthcare outcomes through data services. So this involves releasing synthetic data for broad use by analysts, researchers, healthcare practitioners, and pharma industry. This is called the Simulacrum and is based on 1.4 million cancer patients in England. And HDI has access to this underlying data through its partnership with Public Health England, and so abides by their guidelines for data use and release. Next slide, please. So I really hope that today I can contribute to this workshop on 2 points. I hope that I can prove that there are indeed real benefits to using synthetic data based on our example of the Simulacrum, and also that real impact can be achieved through partnering with external companies and facilitating collaboration between data scientists and healthcare professionals. So now I will speak a bit about the Simulacrum, focusing on 3 aspects. First of all, the data that it's based on and our access to it, the synthesis process, and then finally the services that we offer surrounding that data. Next slide, please. So the data that we're interested in is collected by the National Cancer Registration Analysis Service, or NCRAS, that is within Public Health England, and specifically 2 of their data sets that they collect. So the first is the Cancer Outcomes and Services dataset, or COSD. This contains information on all patient and tumours for patients that are diagnosed with tumours in England. And then the Systemic Anti-Cancer Therapy dataset, i.e. SACT, and this contains information on all systemic treatments that these patients receive from NHS providers. So these treatments include things like chemotherapy, immunotherapy, and hormone treatment. So these 2 data sets are stored within the Cancer Analysis System, which is managed by Public Health England and used internally by their own analysts. And through our partnership, we at HDI can access both of these data sets. Next slide, please. So the Simulacrum is a synthetic version of both data on COSD and the systemic treatment data in SACT, in total on cancer patients diagnosed between 2013 and 2015, so 1.4 million patients, and includes 7 data tables across the 2 data sets. The development of this data lasted over a 2-year project for the first release from 2016 to 2018, when it was publicly released on our website. Next slide, please. So this is what the simulacrum looks like. We have on our left the patient and tumor tables that contain all the characteristics of the patients and tumors, and then the remaining 5 tables contain all the systemic treatment information, such as which regimens patients receive, the cycles of those regimens, and then the details of the drugs administered. Next slide, please. So when we were choosing the synthesis methods, there were 2 things that we wanted to focus on. First of all, the use case of synthetic data. What will this data be used for? And then also the privacy aspect. How can we protect the privacy of our patients? So we identified the main use case to be patient cohort identification and then statistical analysis of that cohort. So that would generally start with a feasibility assessment within the data. Is this patient cohort available? Are there enough patients to do statistical analysis? And how much missing data is there? So after this is done, then we can go forward to create queries that actually perform the statistical analysis of the cohorts. So with these points in mind, we aim to preserve the characteristics in the data when generating our new data set. So this would be to capture strong correlations between data variables, realistic ordering of tumors and treatment events, and also to have the same data structure as the real data. And then finally, we want to enable easy privacy evaluation according to the Public Health England data release guidelines. Next slide, please. So this is what the synthesis process looks like overall. So we have our raw data, and then we start with a correlation analysis of the pairs of data variables and choose the important ones we want to keep. Then we represent this in a probabilistic graph, which is then used for data generation. And once we have our synthetic data, we validate it before release. Next slide, please. So I'm going to give like a simple example to try and illustrate how this is done in practice. If you imagine that we have our real cancer data on the left, and we want to create a new synthetic data set. So fill in all of the information in this blank synthetic data set. So we would look in the real cancer data, find all those strong correlations between pairs of variables and try and recreate those in the synthetic data. Next slide, please. So what we would do is we would find all of those pairwise correlations and select the correlations that are above a predefined threshold, so all the strongest correlations, and represent them in a graph like this on the right. So here, each vertex is a column variable, and then each link represents a strong pairwise correlation. And we assign direction to these links in order to help us when we're synthesizing the data. So it tells us the order in which we generate the columns in the data set. And the ordering is chosen by the degree of each vertex. So site comes first as it has 3 links, which is the most number of links. Sex and age both have 2 links, so they come next, and then stage is generated last as it only has 1 link. Keep in mind that this isn't a causality graph, it's just a useful representation that we use for generation. And then with this, we calculate the empirical conditional probability distribution of each column variable, conditioned on its parent variable or variables. Next slide, please. So this is a visualization of what actually happens. So if you remember, our data set on the right was empty before. We would, for each patient, each synthetic patient, we would randomly sample values for each of the column variables, starting with site first. So for each synthetic patient, we would randomly sample a cancer site based on the distribution of cancer site in the real data on the left. And then this is followed by generating sex, which is conditioned on the cancer site, followed by age, which has 2 parent variables, so it's conditioned on both cancer site and sex. And finally, generating stage, which is only conditioned on cancer site. So this should hopefully preserve all the strong correlations in the data. But there's another thing that I would also like to highlight here, which deals with the privacy aspect. So if you look at our first synthetic cancer patient on the right, it happens that the sampling process sampled a lung cancer male patient. And when we are generating the age for this patient, normally what we would do is we'd look in the real data, and as you can see, there's a single lung cancer male patient, and it would mean that we would directly replicate the age for that patient. So without any privacy checks, we would generate a 42-year-old lung cancer male patient, which is something we really want to avoid doing since it's directly recreating patient information. So what we would do actually in practice is we would merge the lung cancer male patients with the prostate male patients and then sample age from the joint distribution of those 2 groups. So it would be a value of between 42, 44, and 45 shown in the real cancer data. Okay, next slide, please. So once we have generated our synthetic data, we need to assess it by PHE guidelines, and these are outlined in this anonymization standard that can be found online, publicly available. So every single data release that Public Health England signs off has to follow these guidelines. And this will apply to the simulacrum as well. So because of this data generation approach that we have, and because we make sure that we do not sample from distributions of small size patient cohorts, it abides by these rules outlined in this standard and is therefore publicly able to be released publicly. Next slide, please. So now that I've talked a bit about the simulacrum, I will talk about the services that we offer through partnership with a company called IQVIA, which works with the life sciences as a data science consultancy. And typically the workflow involves 5 steps, which I'll explain in the next slide. Next slide, please. So this is what the workflow looks like. First, HDI will generate and release the simulacrum, which will then be available for use by IQVIA to explore the data, develop code to do statistical analysis that's relevant for the projects that they have with external clients in the life sciences industry. And then IQVIA will pass that code to Health Data Insight to run on the Public Health England data. So HDI will then get the real results back from the real data and then apply any statistical disclosure controls. So making sure that it's fit to be a data release. This usually involves suppressing small counts of patients, and then they will return these results back to IQVIA, who can deliver them to the client. Next slide, please. So outside of this service, we also provide simulacrum for download on our website. This shows a rough breakdown of simulacrum downloads out of approximately 300 registered downloads since 2018. So this involves the academics, pharmaceutical companies, and government agencies. Next slide. And then also the reason for downloading the simulacrum. This is primarily treatments research. We also have a large percentage of other, which we are currently investigating as what that actually means. Next slide, please. So I'd like to highlight some of the benefits and challenges of our experience with synthetic data. First of all, the simple data generation model we've chosen is easy to implement and leaves us with a full relational database that links multiple data sets and means it's a really good fit for the intended data exploration that we identified in the use case earlier. No major challenges here, but we expect there will be more challenges in the future as we add different kinds of data to such a database as a simulacrum, especially when it comes to sequential events, as at the moment we use simple Markov models, but it might require more complicated data generation methods to capture those complex treatment combinations over time. In terms of information governance and privacy, because of the transparency of the method, it was easy to assess by the Public Health England guidelines for release. One thing that we need to keep in mind, though, is when we release further versions of the data set, if it's based on the same patients, then we need to be careful and ensure that we protect patient privacy. And this is generally an issue that would apply to most data generation methods, and I think would require deeper consideration by the community as a whole. Next slide, please. So we've also found that the setup through IQVIA has allowed us to increase the use of simulacrum, kind of takes that off our hands a bit and allows us to just focus on the synthetic generation aspect. Outside of this setup, there have been challenges in increasing awareness and also identifying additional use cases. In terms of training, we have offered workshops and simulacrum guides available on the website. And through this kind of training, IQVIA experts have been able to provide quality services to clients in the life science industry. And one of the challenges we expect is that the type of data that's available is a relational database, which might be new to users, and so might be the kinds of tools that are required for doing analysis. Next slide, please. So some concluding remarks. I hope that through this presentation, I have proven to you that there indeed are benefits of synthetic data, and that it is possible to create true impact through partnership with companies like IQVIA and optimize the use of this PHE data, which is usually locked away from most people. And then finally, I would like to end with that Health Data Insight likes to take a multidisciplinary and collaborative approach. We foster young talent through our internships every summer and aim to bridge science, data science and health services. And finally, we are always open to research collaboration. Thank you.
Many thanks, Laura. That was a really nice use case example. It's encapsulated, I guess, many of the items that we've been discussing today. And I guess we'll let Fran share the screen there with a new question for us all that we believe might be very helpful, and just asking you, the attendee, what do you view as the major challenge towards realizing a vision for commonly available synthetic healthcare data sets? And again, to you, the attendees, we'd love if you could interact with this. And Laura, we have a very interesting question then from one of my colleagues at Oxford, Ben Cairns. So Ben was asking, it said this is a very nice example data set, and Ben is asking that if a new or an unknown pattern was identified in these data sets, which would generate a new hypothesis, wouldn't it then be almost or impossible to test the hypothesis in the original data set, except doing some post hoc analysis? Because then Ben goes on then to ask that the information, the original data set was obviously already used to generate the synthetic data. So then when might the public release the synthetic data risk the utility for clinical research of original data sets? And I'd love to, I guess, learn your thoughts on that.
So if I understand the question correctly, is it that so are you saying that when you're using the synthetic data, you might find certain patterns, and you're asking whether it's possible to validate that against the original data? Is that? kind of
so my interpretation more, and Ben might type in, I'm sure, to help us a little bit there too. So is that essentially then, for example, if one was using it to generate new clinical insights, that's something you might find in a synthetic data set. It's very hard to check then if that might be a real finding or not. And we can't go back to the original data set because obviously the synthetic one was generated from that in some way. So then we need to find perhaps some other completely different data set than to try and do a replication on that.
Well, yeah, so I mean, I think it should be perfectly possible to, if you found this kind of hypothesis in the synthetic data, then you could actually go to Public Health England and say, would it be possible to run the same code on your data and see if you get the exact same conclusion for the hypothesis? And then they would be able to release that as an official data release.
And perhaps I'm thinking more so that, I don't know, if, for example, then I find, let's say, that one, perhaps people of a certain age and a certain ethnic group have an increased risk of being readmitted to hospital more quickly after having esophageal cancer. If I found that as a new, I guess, hypothesis of interest, how might I then follow up to see if that's something real or is just some artifact in the synthetically generated data?
Yeah, so that's, I mean, it's something that we haven't quite figured out yet, but ideally we would have a system in place at some point to be able to easily validate those hypotheses against real data. Because at the moment, yeah, you're correct in that in the synthetic data, you might have findings that could just be a random kind of creation throughout the generation process. But ideally, we would want to have a way of validating all of those things.
And if I may ask a question, I'm very specific then to your talk. So you've obviously worked very closely on Public Health England, dealing with 1.6 million people's data thereabouts. Would you mind just elaborating a little bit more then on what privacy checks that Public Health England and the data provider wanted before it was potentially okay to release that data set? And if I just may expand a little bit on that question, so because you give a very nice little use case there on obviously it was just a handful of variables, so I'm sure were more variables considered than just that small handset of variables. So I'd just love to know the privacy requirements or requests that Public Health England made of you.
Yes, sure. So generally when we have a data release, it has to abide by that standard I talked about, which you can find online. I'd recommend having a look at it. But essentially what it does is any data release, it has a look at it and looks at what patient attributes are involved in that release. And then what is the size of the patient cohort on which the analysis has been done. And based on those two things, it will require that you either drop or mask certain results because the patient cohorts are too small, and they usually use a K anonymity, and that K anonymity depends on how sensitive the data is as well and which attributes are being involved. So when I was talking about how the distributions that we use to generate the data, when they're based on very small patient cohorts, then that's not sufficient for PHE release. So we ensure like a minimum size of the patient cohorts, basically.
Thank you very much, Laura. I'd love to ask some more questions, but in the interest of time, we might have to move on, and we'll be. If I may, I'll ask you another question or two. Then, if we have time in the group discussion at the end. So thank you very much, Laura. And with interest, and as I look at Fran's screen here. We didn't try and stage it this way, so I think it's just pure coincidence. So thank you to the 23 people who responded to the question. And it's just really hard to define what a privacy evaluation metric and that's why I'm delighted that we've got Alan Tucker speaking next, talking a little bit more about this question of how do we ensure patient privacy. Alan has worked very closely with Pooja, who gave the talk at the start of this workshop, and has worked very much hands-on with a CPRD data release. So Alan, will hand over to you, and I very much look forward to learning your thoughts on this topic.
Great, thank you very much. And thank you very much for inviting me to a really interesting afternoon of talks. So I have been given a title for my presentation, though I will be honest that I've been a little loose with it, and I skirt in and around the privacy issue, but I do address some of the points, and I also try and address some of the other points actually that have been discussed earlier. So it's quite nice sometimes being the last speaker. So I'm from Brunel University, where I head the Intelligent Data Analytics Group in the Department of Computer Science. As you heard earlier, Pooja described very nicely the project that we've been working on from a data custodian point of view. What I'm going to do is talk about some of the topics from a slightly more technical perspective, but I'm trying not to go into too deeper technical level. So hopefully there's some people who aren't familiar with some of the techniques. I'll try and be high level enough to keep your attention. So next slide, please. So we can jump this in some ways. So we know some of the justifications for the need for synthetic data. It's still quite open, judging from some of the questions that we've had earlier. The idea that synthetic data can be used in many different ways, but one of the key things that we have seen over the last decade or decade and a half is a real difficulty in making gold standard ground truth data freely available for institutions like universities to be able to learn from them, and so there's a clear need for this exploration, this idea of trying to build synthetic data sets. Next slide, please. And so the idea of synthetic data should, in theory, or we hope, help us get around some of the privacy concerns. And there's some important privacy concepts that apply to just anonymized data as opposed to specifically synthetic data. And we do have to pay attention to some of those concepts. Michaela nicely talked about, for example, differential privacy. This idea of being able to remove an individual data point, so an individual patient, let's say, from an analysis, and it should have no clear, direct, obvious impact on that analysis. And she also highlighted the risks of this, of repeatedly requesting for aggregate data, and specialist algorithms and hackers who can actually do this. And it's been proven that you can still identify individuals from those multiple requests of data. But also the impacts of rare cases, and this has been highlighted a little bit. I think this is really important as well for synthetic data. There is a trade-off, which I'll try and talk about a bit later on in this presentation. The things that lots of machine learning people are interested in doing, and you've all heard it, is personalized medicine. Now, personalized medicine is about focusing on very specific, smaller numbers and smaller cohorts of individuals. And by definition, that's a riskier thing to do if that's the data we need, more easily identifiable. And then the other important privacy concept is k-anonymization. So this idea of if we remove certain key fields or generalize certain data points, can we make data anonymous at a particular level? So can we say, well, we only know it's one of k possible individuals? But the question again that's still wide open is, what's an acceptable value for k? And also many of the data sets that we see, particularly the stuff that I've been working on with Pooja in CPRD, is these are high dimensional data sets, and k-anonymization is not easy if you are having to remove large numbers of fields when you've already got huge numbers of dimensions. So these concepts, which have always applied to private ground truth data, are still really important for synthetic data. Next slide, please. Okay, so we have to talk about GANs. Mihaela's not here. I was going to be controversial, but she's left, so I don't have to be. So lots of people, there's a large interest in GANs for trying to model synthetic data. So these are essentially deep learning approaches, which are extremely good at kind of clamping down on very precise distributions and relationships within a data set. And clearly, as a result of that, they're very suitable for learning models that can generate synthetic data sets. However, I advised in some ways the group to avoid this. Actually, I had quite a lot of people on my side already, I think. We were very nervous about generating a model from data, inferring a model from data, where we had very little transparency. And Pooja alluded to this in her presentation. We really wanted to make sure that we had quite a lot of control over the synthetic data that we were generating. And we had some expertise as well in terms of people who knew what kind of relationships we should expect. And as a result, we moved away from the idea of a GAN, which is still considered in some ways a black box model and not as interpretable as some of the other approaches that have been discussed in the talks today. Next slide, please. So, as I said, the impact of having a black box model can be considered risky in some ways, I think. So if we start generating synthetic data from a model that's been learnt from a data set, which could be huge, we don't always know what are the biases involved with that. So we have risks of inductive bias in generative model learning. And there's still a lot of work that needs to be done, a lot of research in understanding that bias, particularly in deep learning models, but across many machine learning approaches. The data itself holds bias. We know that most data analysis is secondary data analysis. It's been collected for different reasons for the analysis that it's being performed on it. And therefore, we need to be aware of those biases, and just throwing it into a generative model can be risky too. And then lastly, of course, society. And we've seen from COVID and many other examples too, the biases that there are in society in labeling data, in diagnosing and treating different subgroups of people in society. So it's really important, and it was important to us that the models that we chose to infer and then generate synthetic data from were as transparent as possible. So we wanted to know what dependencies were represented in the model, and can we confirm known relationships and also highlight relationships that shouldn't be there. Next slide, please. So as a result, we looked at a whole suite of models known as probabilistic graphical networks. So Johnny talked about Bayesian networks, which were the one that we really focused on. And Bayesian networks are incredibly flexible, and the whole family of models are very flexible in what they can do. So firstly, you can infer these from data, but you end up with this nice network structure that you can query, as well as just interpret and visualize. You can actually enter queries into that model and see what impact those queries have. So you could say, okay, I know I want to understand a bit more the impact of a particular disease or set of symptoms in a particular region or on a particular age group. And you can enter that information onto a model that's been inferred from data and understand by exploring some of the posterior distributions over the other variables that the behavior within your data set. So it's very transparent in that ability to query evidence and interact with someone. So we exploited that, but also they're very flexible in what they can model. So they can also be extended into the time domain. So we can have dynamic Bayesian networks or the whole family of state space models, like the hidden Markov model you can see on the right here. And so we really saw these as quite a flexible approach to being able to interact with the data we've got before we started to actually generate synthetic data. Next slide, please. So what we did was we inferred from the CPRD, or from a subset on cardiovascular risk, as Pooja mentioned, these network structures and models. But what we also identified was some of the weaknesses of these approaches, and I think Johnny did mention this as well, that they don't always capture as closely the distributions and relationships as some approaches like deep learners. But there are techniques for incorporating latent variables into these network structures in a very graphical and transparent way. So we exploited some of these approaches, and you can see on the right here a typical network structure that we inferred, and there are certain latent variables in there. I think there are 6, so L1 to L6. And they've been inferred, so you can actually see where the unmeasured effects are influencing known variables within our data set. So in this way, we managed to exploit some of the factorizations that you see in deep learning, but preserve as much transparency as possible. Okay, next slide, please. Not sure if this all came out too well, but so what we did, and in that Nature paper, as well as in an ECML conference paper, was we explored the fidelity tests. So we looked at, firstly, simple correlations between known relationships that we'd expect there. We looked at distributions, so univariate distributions, and we wanted to see whether the latent variables actually helped us to get closer to the ground truth distributions, and they did. But we also looked at joint distributions. So beyond univariate, we looked at second order and third order joint distributions. So we could actually see how the distributions and the variables interacted with those distributions. And then, so in some ways, I think the stuff that Johnny was talking about in terms of quality and fidelity, we were testing in this way. And then the utility idea that Johnny was talking about, we explored by actually assuming that we had this synthetic data. We wanted to see how it performed compared to the original ground truth data when we actually wanted to validate and assess and train and infer machine learning models. And so hopefully on the right, you can see what we have overlaid is the ground truth data and our synthetic data. And this are ROC curve analysis and precision recall analysis for a number of different machine learning classifiers. And what we found was a great deal of overlap, not just in terms of the areas under the curves, so the accuracies, the sensitivities, and the specificities, and the recall and precision, but also in the general shapes of these curves too. So we seem to be capturing quite a lot of the nuances when it came to actually developing and assessing real machine learning classifiers using our synthetic data sets. Okay, next slide, please. Now, when it came to privacy, what we decided to do, first of all, was explore a number of different concepts. And these overlap quite nicely with some of Mihaela's epsilon identification metrics. So we wanted to explore the effect of sample size and the number of variables that we had on the chance of actually generating clones, so collisions, as someone else put it, as well as this concept of inliers and outliers. So you can imagine an outlier in a ground truth data set is at risk more of being identified than an inlier. So someone who's kind of sitting in the data space surrounded by a whole population of similar people. And so those outliers are really important things to identify. Whereas a clone is is a piece of synthetic data that just by chance is identical or as close as identical as matters to a ground truth patient data point. And what we found was we did repeated resampling from our underlying models, probabilistic models, and we wanted to see the impacts of the ground truth size on seeing outliers, inliers, and clones. And we found, unsurprisingly, that as the sample size gets bigger, the chances of clones actually goes down because there's more ground truth there, but also the probability of outliers becomes reduced as well. And this is almost just a side effect of the sheer size of the data that we have to play with. So the more data you have, the less chance you're going to have a single individual data point, one person sat by themselves. So the more you throw data at it, the more they become a population in a particular region in the data space. Okay, next slide, please. Okay, and this is just slightly building on what Pooja was talking about, where we did actually get someone within the MHRA to simulate an attack. So we gave this person a load of selected ground truth information about patients. So this could be things like the age, where the region that they live in, whether they smoke or not, their gender, so sorts of things that people may be able to get access to. And then we wanted to see how likely it was that information could be used to link to outliers in the ground truth data. And what we found, interestingly, was even as you added more attributes to help that person try and find out an individual, we didn't really see much increase in the chance of linking those ground truth set of key attributes to real ground truth data points. And as Pooja said, when we did, the distance was still there. They weren't overlapping, and in fact, they were quite distinctly different. So the example here is someone who has a very similar age to a synthetic data point. So you can see that the ground truth, we have the age is 88, and the synthetic was 86. The BMI is very similar, blood pressure very similar, both similar smoking status and female from the West Midlands. But actually, when we come to the synthetic data later on, the synthetic omits the fact the person has had a stroke and they have different cholesterol ratios. So it's still not a smoking gun that we've actually found a match there. And so we were quite impressed actually at how difficult it proved to be to identify individuals when you have large samples of ground truth data. Next slide, please. Okay, and so as a result, I'm kind of repeating again what Pooja said earlier. As a result of this research, we've managed to release the cardiovascular synthetic data and COVID-19 data thanks to NHSX. What I'd also mention quickly is in the ECML conference I've not covered here, we did some very similar experiments extending our methods into the time domain, where we explored models from the MIMIC database that Mihaela mentioned, where we were trying to model blood pressure over time and using probabilistic graphical models in exactly the same way. It was actually a form of hidden Markov model, dynamic Bayesian network hybrid, but we had very similar results where we looked at not just correlation structures, but we looked at dynamics, cross-correlation functions, and it showed quite nicely how these methods actually extend into the time domain quite nicely too. Okay, next slide, please. Okay, so just to summarize, it's clear that synthetic data from our experience with the CPRD data has a lot of potential in dealing with some of the problems of privacy, if not all, and that there's a class of generative models that offer a lot of promise. So whether we work with GANs or whether we work with probabilistic graphical models, they both seem to capture the fidelity of those underlying data sets. But there is always going to be this trade-off, and this is what I mentioned at the beginning of the talk, this trade-off between utility and privacy. So the idea of, at what level do we want to aggregate the data, and how personalized do our interventions want to be? So if we want to try to build interesting analyses and models, machine learning analyses and models of small cohorts to do personalized interventions, or if we want to model rare disease, or if we just want to marginalize over a large number of features, then we do more and more run that risk of identifying a smaller and smaller cohort, and therefore run more and more of a risk of identifying people. So that's always going to be a risk that synthetic data won't completely remove. What I think we've managed to do, though, with this project is really nicely generate synthetic data, high fidelity synthetic data. The risks of privacy are still there, but small, I would say. But what we've also done is dealt with bias head on. I think in the Nature paper, something that Pooja and her team did fantastically was pull apart the networks that we'd inferred from the data, and literally just, you know, link by link, independence by independence, you know, we backed it up with publications and identified ones that seem to be unusual. And I think that's a really key thing that we do need to be aware of when we're generating models that we're going to use to generate synthetic data from. Okay, next slide, please. Just to say thank you to all of the people at CPRD and MHRA. It's been a really valuable experience for me, working so closely with practitioners who have so much amazing data available to them. Thanks a lot.
Many thanks, Alan. That was absolutely fascinating. And if I may ask a question around the GANs and just provocatively push you a little bit on that. Does it matter? Yeah, I may provocatively ask, does it matter much whether we can interpret how the synthetic data is generated? Because if we have, for example, a good set of evaluation metrics and tests to check the data seems sensible, that it maintains univariate, multivariable correlations and meets some privacy tests, then in some ways, if I may naively ask, does it matter then that we can interpret how that data was generated so long as it meets particular checks, pre-specified checks and requirements?
It's a good question. It's Jeff Hinton, the kind of forefather of deep learning's put that forward as a thing. Who cares if it works? I think it does matter. So you could imagine a scenario where you did infer a network model, let's say, where you can see all of the relationships, and that network model puts in a very problematic relationship because of the way data has been collected. So it could be that, you know, there could be a link between a particular ethnic minority and a particular condition that's only there for, you know, completely spurious reasons, the way the data was collected or some other reason. If you hardwire that into your model when you learn it, so that could be an embedding or weightings within there, there's a responsibility, I think, on the person generating that data to know that they've hardwired that into it. I'm not sure what the legal status would be of that either. And I think what we've been looking at with our approach is actually to say, well, we can actually say we don't feel comfortable with that relationship being in the data set. And so you might be right, maybe it doesn't matter. But I think there is kind of a responsibility as someone who generates synthetic data to know that you are generating data in a way that you know isn't biased.
And then coming on to the, for example, the privacy checks, I think it's probably inevitable, is it, that they're generally kind of a priori defined, and probably for different synthetic data sets, we will have to, there's still a lot of background knowledge that's needed then to construct what the privacy checks are, or do you think is there something that might be more broad and generalizable across that? I'd be quite keen to hear your opinion on that.
I think it's always going to be application specific. I think there'll be certain applications where we can use certain approaches to privacy and others where others were more. I think the idea of coming up with metrics is still a very, you know, it's a field in its infancy. But I think it's really important that we do that. Things like differential privacy, so PrivBase, which is an approach using Bayesian networks, which adopts differential privacy approach to learning Bayesian networks, is quite interesting because what it's doing is, you know, quite a classic approach to privacy and bringing it into the machine learning fold. So I think there's certain concepts that we can use, but there's going to be definitely a need for new metrics specific to what we're going to be doing with the synthetic data. Yeah.
And if I may ask one last question specific to your talk, it was a question that Gillian Rabb had asked earlier, or somewhat paraphrasing Gillian's question, is for the synthetic data release, did you go with roughly the same number of participants as is in the real data set, or were you tempted, I don't know, to say, well, let's generate 5 times as many participants? And was there really rationale behind the decision to go for that? So the ratio of amount of synthetic data to the original generating real data set?
So Pooja will be able to answer that question better than me. But
Okay.
what I will say is we have explored generating multiple different sizes of data. And something I didn't mention as well was this idea of conditional data generation. So the idea that you can say, okay, I just want to generate a load of data specific to people over 60 who live in the northwest of England, which is something you can do with this approach. But Pooja, yeah, maybe you could answer the question. The final release, I think, has a similar amount. Is that right? Or
so the 2 data sets which are available from us, they have the same amount. So it's a 1-to-1. However, we have for some of our other data sets, which we have generated synthetic data for, it is up to 5 times the number. We haven't observed a difference in the privacy so far, but we started off with large sample sizes, fairly large sample sizes. I think the smallest we had initially for the CPRD data was 90,000 patients, though we did other experiments to demonstrate that we could deal with heterogeneous data sources. So like Alan mentioned, we did some tests using the MIMIC data, which is openly available. There's an Indian liver patient disease, which is a data set, which is a really small data set. And we use that to demonstrate that we can boost sample sizes and still preserve the distributions in it.
Yeah, I was just wondering if, apologies, Gillian, if this is not what you sort of meant. I'm just wondering if the question here was, and this is of particular interest to me, who works with rare diseases, which is the concept of, why is it better? In other words, so you could generate, you have 500 patients in a real data set. You could, in theory, generate something that has the same distribution that has, I don't know, 5,000 patients. But given that it came from the original 500, why is it better? You just now have a smoother distribution, but it's based on the original one. And I guess that's part of that. Hopefully that's part of Julian's question. So in other words, if you take the original fidelity, you can interpolate, if you like, but you still start. It's a bit like with an image, I guess. You can only work with what you had to start with. And I think that's, that's one of the interesting things, and that you can make bigger data sets. And I guess I can see where there is absolutely value for testing an API, or, you want to do something technical where you want a large amount of data. But in terms of the clinical application, do you have any views on that? So if someone asks you for a much bigger data set, why would you do that? You could do, but why is it?
Again, this is something that it's a valid question, and it's a question we've asked ourselves. Is it of any value? Are we going to generate meaningful information and meaningful differences? Because that's what you want. You want the differences to come about. And we'll just have to explore this and see. Now, the advantage we have is we can run these tests by using a larger sample of CPRD data, and then testing against a smaller subset to see if we generate synthetic data using the smaller subset, can we actually get to the distributions in the larger subset? So that is something we are exploring right now. The other thing we have to we had questions about is maybe there is a certain value, like there are diminishing returns with everything. Maybe if you have a certain threshold of information, that is sufficient, and beyond that, it doesn't add much value. So actually, you could generate the larger numbers that were needed. But really, very pertinent question. I don't have a conclusive answer. That's why we're doing these experiments.
Very helpful, and I'm just quite keen. First of all, I should point out, Gillian helpfully sent me a message that I didn't ask her exact question. So Gillian, I was using your question as inspiration for my own, so I should have been more clear in saying that. And your question is, yeah, very helpful and explicitly mentioned in the Q&A. And what I was very keen on was to ask Pooja, Laura, and Johnny in particular is, for example, seeing the talks today by, say, some of the, for example, methods developers. Is there anything in those talks, for example, that you might have seen it say, oh, I wish I would have known that when I started off in my journey in releasing synthetic data generation activities, or I'd just love to hear your reflections on what you think we might benefit from by, I guess, more interdisciplinary working, although obviously I do recognize you have technical collaborators already on board. Maybe we'll go in order of Pooja, Johnny, then Laura.
So when we started off this work, the first thing we did was look for who was out there, because we didn't want to duplicate what others were doing. In fact, partway through the project, we found the simulacrum data. So, you know, we read the methods. We had a brief conversation with Jem, Rushpass. Johnny, I think you were in a, like, you know, there were these early knowledge sharing sessions, which Alan and Zenshan, who are part of the CPRD team, were also present in. So yes, we would, you know, this is not one of those things where it's about, you know, you showing that you're better than anyone else. It's an area where we genuinely need to work together.
I suppose sort of going similar theme from what Pooja just said there about what we were thinking when we first started. I was actually thinking if everyone else is looking at particular areas, I want to look somewhere else. So I'm interested in the gaps, and I'm still interested in the gaps. It's still the question which I'm putting forwards across government at the moment is there's lots of research going in a whole variety of areas. Where are the connecting bits, which are maybe a little bit more boring, but that's the sort of stuff which I can fund, and then something which enables all the other bits to connect and talk to each other. So yeah, connections, talking. So it's not so much I'd like to know what's out there in terms of methods. It's more why doesn't this particular why don't the people looking into differential privacy, why hasn't that been applied more widely to this particular technique? And why is it so difficult to apply these techniques to longitudinal data? What's the gap? What needs to be done? And if it is the boring work, we'll get that done so that everyone else can get on with the interesting work and actually bring it all together.
So I think with Health Data Insight, we kind of thought about the use case of the actual synthetic data, because in a way, this is one of the most important things when you're considering how you want to generate the data, because it needs to have the correct properties. So I think we were looking at all of this data held by Public Health England and thinking, this is such a rich and amazing data set that no one can access. So what is the best way to increase this access? And in the end, we found that the best way would be to create synthetic data as a tool for the development of analysis queries, and not necessarily for clinical like final decisions on clinical research, because the results from synthetic data are never going to be completely reliable. So I think yeah, that's what our approach. How can we use this data? And I think it would be interesting to come together as a community to figure out what other use cases there could be, and therefore what methods would be required for those use cases.
Can I also add slightly? Yes. Just it's again another sort of gap between the academic side and the architecture side. So we usually try to connect the academic with the sort of industry. But actually what I'm finding is the people that are most interested in synthetic data that I talk to on a weekly basis are the architects, people who are piping data around the NHS. And there is a whole community of synthetic data going on over here, which is architect related. There's then some practical industry users in the middle, and then there's a whole load of academic. And again, that connection between those, it's weak between each set, but it's even weaker, I think, between the architects and and academia. So I'm talking about, they're looking at agent-based models because the data that they need to know where it's come from and where it's going. They don't just want to see a snapshot. They need to know history of the data, messaging and all this sort of stuff as well. And so the actual use of the data is very different to what's being produced in the academic papers.
Thank you, Johnny. And we'll hand over to you, Neil. So I think we're getting towards the
end.
end.
We're getting near to the end. So first of all, just a massive thank you to all of the speakers. It's been excellent, and all of the participants. I'm sorry that people have had to just put things in the chat, but once we get more than a certain number of people, it gets a bit wild if it just becomes a Zoom meeting. Just from my perspective, from the sort of, if you like, from the HDR UK thing, I'd be really keen to get feedback from suggestions, but a few kind of thoughts from me, and then I'll pass over to Aidan to finish. So the first is, one of the things, so what can HDR UK do here that's useful and may add value? So one thing, as you just mentioned, Johnny and others have mentioned, is this thing around community and networking. Actually knowing that other people are doing or have done something similar, that you can ask and say, well, you use this technique, why did you do that, and how may it work for us? One thing seems to be around, perhaps we might be able to do something to rationalize a bit around the learnings from everyone, around the governance and the privacy and the IG perspectives, to make that almost an HDR UK, you know, you could almost have a recommendation. These are the ways that other people have tried to approach this. You're just putting things together. There is something I think that's still quite interesting around having, if you like, the rational overview of why people chose particular techniques, because there seems to be quite a lot of people that, you know, there are several options as to how you could come up with not the same, but a sort of a similar type of end result, and why are one technique chosen rather than another. There is definitely something I think that potentially we need to consider from HDR UK perspective about making synthetic data sets available. So can we just make them available potentially, or at least findable or available through the gateway? And almost linked to that is this fundamental thing of getting some kind of semi-agreed metrics or measures for how good a synthetic data set is. Now, I know that's quite hard what the good means, but how well does it represent the distributions in the original data set, or how confident are you that it does, etc., etc. And then I guess the very last bit is for everyone, in that, are there areas that are sort of, I don't want to use this term because everyone uses it before, but the equivalent of a kind of grand challenge in the synthetic data space, that it's worth us pushing from an HDR UK perspective, that we might be able to in future get some push for some funding and some collaborative work. So I'm going to leave it there, but look, it's been really super interesting. I think there's loads of really good things, clearly lots of interest and lots of work going on in this space. Just as an observation, I'm really quite surprised how few people were working on, for example, synthetic imaging data, just because that seems to come up all the time, but most of the data today has been sort of population-based data. And lots of other interesting things which I haven't got time for. But Aidan, over to you just to sum up and maybe around potential next steps. But thank you to all the speakers.
And yeah, similar to Neil, I'd just like to echo my thanks to all the speakers and to Fran and Cara for doing a huge volume of work in organising this. And as Neil said, there is a lot of efforts going around in the imaging space, and particularly around retinal imaging and synthetic data generation of that. And to you, all the attendees out there, I'm sure there's many other efforts going on in the synthetic data generation space that we have not showcased today or might not be aware of. So we would really value any suggestions that you might have, or other projects to make us aware of. As we're very open to collaboration and getting, I guess, as much diversity of input as possible. So I'm going to stop there and give everyone just a minute back in their days there, so because I'm pretty determined that we should stop by 5 o'clock. So please do, if you've got any suggestions on next steps for us, or other projects or efforts we should consider, please do get in touch with Neil and myself.